Let me see. Yeah, it's like just a little because I woke up this morning.
Should I go ahead and share my screen?
You can, sure, you can do that if you like, just to test. We've got 4 or 5 minutes. We'll probably have an announcement or two before you start. And
okay, no need to test. I'll just wait.
Yep, great. But yeah, if you wanna share and test it, go right ahead.
Okay.
So we've stopped sharing, right?
I guess if he wants to, yeah.
Yeah, I tested the keynote.
He came right up. Actually, there he is. I don't know what's. Oh, that's there. He is in blue jeans. So we just have to. It's fine. Someone just started. That's the blue jeans, and so we're fine. Yeah. Okay. Where's my cursor? Is it? Oh, it's on here now. So we gotta move. I think we move it this way. Yeah.
So it's off that way.
I'll have to go find that later. I hate this. That they don't let us. Apparently, if we don't do this, then it displays that bar. Oh, right there. There we go. Look at this thing right here. Well, I wanted to just move it, and I can't. Okay, there we go. I have to do it by the thumb click. So this is the
one section of exoplanet and solar system. Okay.
Yeah. Right here is all construction.
Like, I had no idea what was going on. Okay. So we take it out. Like, I checked the keynote. It looks fine. Yeah. I think she was perfect. Sinclair, your and then negative 10 off. So that's kind of yeah. Wait this morning, and I apologize. I'm not sure. Yeah, she was remote, so I could. It was so cool. Yeah. But yeah, that was super cool. One more like but it pushed them to like rest
actually.
Yeah, but they were yeah, it was very solid.
Good morning, fellows and associated people. Two things. people, there's a few more sign-ups for the open mic, which is awesome. Please feel free to sign up if you have anything you want to share. We'd like to have that kind of final list by tonight. And as far as the tours go, you realize the tours are not compulsory. If anyone really just doesn't feel like it or can't make time for it, that's fine. There is one person or two people who would like to take the tour, and all the slots are currently filled. So that's all I wanted to say. And you can email NHFP about that. And Jake is the chair for this morning's session, so take it away.
Everybody. So Diana, you're up first, and I'm going to give you a 2-minute warning. Just say 2 minutes so you are aware of your time. So.
Okay, that sounds great. So does this look good? Can it be seen? The slides are good? I'm good to go?
Yes, we can see.
Okay, awesome. All right, so hi everyone. It's great to see you all virtually at least. My name is Diana Powell, and I'm a Sagan Fellow at the Institute for Theory and Computation at the Harvard Center for Astrophysics. And today I'll be discussing some new work on 2D microphysical clouds and exoplanet atmospheres. And here, when I say 2D, I'll be showing clouds calculated as a function of planetary longitude and atmospheric height. And these new models allow us to understand the interplay between first principle cloud formation processes and atmospheric dynamics. And before I really get going, let's talk about why clouds are crucially important to study and understand. So we all have some intuition about clouds from our familiarity with clouds on Earth. But clouds are also important beyond Earth and are in fact the dominant opacity source in most planetary atmospheres. So clouds are important tracers of atmospheric physics, such as mixing and transport. Clouds regulate the planetary climate through regulating radiative transfer and chemistry. And clouds must be understood when determining atmospheric abundances. Also, often the clouds in an atmosphere are the only thing that we can see. So it's therefore an absolute necessity that we understand clouds when we are interpreting planetary atmospheres. And so I've just shown some cloudy objects in the solar system, but clouds also appear to be abundant in substellar atmospheres. So here I'm showing the classic collection of transmission spectra of 10 hot Jupiters, where many of these atmospheres have damp spectral features or flattened or sloped optical spectra, and all of which is indicative of some optically thick absorber of stellar photons like clouds. And now James Webb has also shown us that even atmospheres that were previously thought to be clear with no significant cloud opacity still have spectra that are shaped by clouds. So here I'm showing one of the JWST ERS transmission targets. So this is WASP-39b, where we need the addition of some non-gray cloud opacity to model the spectra. And stay tuned for much more on this planet. But yeah, we need clouds. And clouds have also been observed directly in the atmospheres of planetary mass objects. So here I'm showing another brand new JWST emission spectra, well, this time emission spectra, of the planetary mass object EHS 1256b, where there's this broad absorption feature in the infrared that's not captured by the model shown here, that is likely caused by silicate clouds in their atmosphere. So clouds are important in shaping the spectra. And excitingly, as you can see here, the model in red and the data have some really significant differences. So atmospheric modelers will have plenty to do for the foreseeable future. And clouds are also thought to contribute to observed spectral variability. So on the left here, I'm showing HST emission spectra of the same brown dwarf at different times, where you can see that the amplitude of the spectral features can vary significantly. So I'm showing a brown dwarf here because they're often thought to have atmospheric properties that are similar to hot giant exoplanets. And here the spectral variability can be nearly 30%, and it's likely caused by clouds that are rotating in and out of view. So clouds often dramatically impact observations of substellar atmospheres. And so I approached the study of clouds using microphysics with the community aerosol and radiation model for atmospheres known as CARMA. And so when I say microphysics, I'm really talking about the first principle physics that governs the evolution and formation of clouds. And CARMA is a really well-tested code that's been applied to nearly every planetary body in our solar system with an appreciable atmosphere, where it has successfully reproduced detailed observations from probes and orbiters. And so CARMA works on this Eulerian grid of particle size and altitude, where particles can grow and move into larger bends, as well as evaporate and move to smaller bends. and particles can also move vertically along this grid. And karma is particularly powerful because it starts from first principles and then calculates the fundamental cloud properties that shape observations. So namely the fully resolved cloud particle size distribution, which is really important. I'll come back to it briefly later. And it does this of various cloud species as a function of time. And so on the right here is a general picture of how karma operates. So here I'm showing altitude in the atmosphere as well as temperature and pressure. The condensable gases are mixed from a reservoir in the deep atmosphere until they reach a point where the gases become supersaturated and cloud particles form via microphysical processes. And then these particles can then themselves be vertically mixed or settle. And now before I briefly discuss microphysics, I want to highlight that the new aspect of the model that I'll be focusing on today is the addition of horizontal advection around the equator of a planet. So in terms of microphysics, there are three key processes of cloud formation. And all of these processes depend on atmospheric conditions as well as other key properties. So the first process is nucleation, which occurs when a supersaturated background gas nucleates onto a seed particle. And you can also have a homogeneous nucleation without the presence of a seed. And then whether a species nucleates homogeneously, heterogeneously, or not at all depends on its specific material properties that come into the exponential term here. Then condensation occurs, where a condensable molecule diffuses along a path until it interacts with a cloud particle and condensational growth occurs. And this is often just limited by the diffusion of the condensable grain of the condensable species. And then clouds can also grow via coagulation, where two cloud particles collide, forming either a larger spherical particle or an aggregate. And this process is often limited in our simulations by number density. And so by considering these cloud formation processes, we can start from a background atmosphere, just the gases, and then calculate cloud properties. And so here's a quick primer of what some of these results look like. So here this is for standard one-dimensional karma. I'm plotting the mass density of condensed cloud particles as a function of particle size and atmospheric pressure. And each of the different colors indicates a different cloud species. And so as you can see, each of these cloud species forms at different times and has different particle sizes and vertical extents. And our results also tend to reach this steady state, as there's some variability which may well be real, like climate cycles on Earth or Venus. And I'm quite interested in this variability, but for now, it's also in the 2D cases, but I'll be talking about 2D solutions for this talk, time average solutions. Okay, so now let's talk a bit about hot Jupiters. So these planets are tidally locked, such that they have permanent day sides and an extreme insolation gradient. This insolation gradient drives a super-rotating equatorial jet that operates to reduce the gradient in insolation, but it does so less efficiently at hotter temperatures where re-radiation dominates. So these planets tend to have very hot day sides, a hot eastern limb, relatively cool night sides, and a cool west limb. And so the atmospheric inhomogeneities on these planets, as well as their high temperatures, make them really exciting laboratories for understanding cloud physics. So here on the right, I'm showing two pressure temperature profiles that occur on the same planet, and we expect that many, many different cloud species will form, and that they'll do so at different heights, and the composition of the clouds will vary at different locations on the same planet. So that's quite a nice laboratory with several potential controls, so a very different environment than here on Earth, where water is the only condensable species that forms. And so while these atmospheres are exciting cloud laboratories, they also represent a challenge for studying cloud formation because the super-rotating equatorial jet will transport cloud material horizontally across the planet to regions with significantly different temperature structures. And the horizontal advection timescale around the equator of the planet is comparable to or faster than the vertical transport mechanisms that control cloud formation. So here on the left, I'm showing the time that it takes for a particle of a given size to settle down in atmospheric scale height based on its location in the atmosphere. And here the horizontal advection time that's pointed out by the black arrow is comparable to that time that it takes for particles to settle in the atmosphere. And furthermore, cloud formation is controlled by the supply of condensable gas from the deep atmosphere, and the time scale of this delivery is shown on the right, where vertical mixing is parameterized diffusively. And throughout the atmosphere, gas diffuses over a scale height more slowly than it is affected around the planet. And the same can be true for cloud formation processes themselves. So here I'm showing average growth and evaporation timescales, so the time that it takes to grow or evaporate a single cloud particle, for 4 different cloud species as a function of atmospheric height and planetary longitude. So on the left, you can see that both growth and evaporation of titanium and silicate clouds tends to happen very quickly and is only rarely comparable to the horizontal advection time. However, if we look at the formation of iron and chromium clouds, we see that their growth and evaporation occurs much more slowly and is often comparable to the horizontal advection time, such that these clouds are slowly growing or evaporating as they are transported along the planet. Okay, so these timescale arguments have demonstrated the importance of considering horizontal advection. And so when we consider this, what do we find? And so here I'm showing cloud particle mass densities as a function of planetary longitude and atmospheric pressure, where each color represents a distinct cloud species. And here each panel is a different hot Jupiter with a different equilibrium temperature. And so at cool temperatures, 6 different cloud species form. I wrote 5 here, but it's actually 6. And it's hard to see on this plot because they all form primarily in the deep atmosphere at the same locations, roughly. Then as we increase in equilibrium temperature, we start to see the disappearance of some cloud species, such as KCl clouds. We also begin to see the deep atmosphere clearing of clouds as the cloud base moves higher in the atmosphere and the upper atmosphere becomes more cloudy. Eventually, we start to see the day sides clear up. Though interestingly, we see that some cloud species that do not form on the day side can still survive the passage without entirely evaporating. So here in this panel where I say day side clears up, you can see the small amount of aluminum clouds that are located on the day side, which wasn't expected from the 1D case. And for some ease of intuition about how these clouds are impacting atmospheric opacity, I've plotted the size distributions of the silicate clouds separately here. And silicate clouds are important because they are typically the dominant source of opacity in the atmosphere, and certainly the dominant source due to clouds, but often the dominant opacity source compared to the gas opacity as well. So we see a similar trend here, where deep silicate clouds are present, or silicate clouds are primarily present deep in the atmosphere, although there's some small particles in the upper atmosphere. Eventually, the atmosphere is covered by a near homogeneous cloud layer in the upper atmosphere, although I note here the particle size can vary with different locations. Eventually, the deep atmosphere clears up, and then at hotter temperatures, the day side clears up. So this gives some intuition about where we expect clouds, the opacity from clouds to really impact the atmosphere. And the formation of clouds also has some other interesting effects, like it depletes the condensable gas species that goes into forming clouds. So this may be observable with high resolution imaging. It may have already been observed. So here I'm plotting the current partial pressure of iron gas divided by the initial partial pressure of iron gas as a function of planetary longitude and atmospheric pressure. And here the lighter colors have a more significant depletion of this gas species. So as you can see, that iron gas progresses from being very depleted in the upper atmosphere across the planet for cooler planets to being only marginally depleted around just the west limb of this planet at hotter temperatures. And then the next step, of course, is to look at the observables we see from clouds. So here I'm showing limb-resolved transmission spectra at a typical JWST resolution with one transit. So separating the transmission spectra on the east limb is something that we can find on the east and west limbs is something that we can finally do with JWST. And this is a work in progress. So very soon we'll see limb-resolved transmission spectra, which is very exciting. And we expect to see many interesting effects from clouds here. So of course we expect to see damp spectral features, which has become a hallmark of observing clouds in transmission. But we can also expect to see a feature in infrared wavelengths that's due to silicate clouds, which excitingly we see this even in the cases where all the other wavelengths are completely damped. So this is really an effect of having a resolved full cloud particle size distribution, where you get opacity from both small cloud particles and large cloud particles. So you can damp the spectra and also make this absorption feature in the infrared that requires small particles. And then there are also many trends that we can pick out from these spectra. So I won't go into them all now, but as a teaser, on the west limb, we pretty much expect the atmospheres to go from more clear to more cloudy as we increase in equilibrium temperature in this regime. So here going
Diana, you're about a minute over, just if you want to.
Oh, shoot. Okay. I will go quickly then. The east limb, of course, looks different. So we go from clear to cloudy to clear. And I'll also say that James Webb will be great for looking at emission spectra and phase curves, where clouds will also have a big effect. And so for all of this, stay tuned. So we'll see great results here very soon. And here's the summary. Sorry, I must have missed the 2-minute.
All right. Thank you. Do we have time for a quick question, if anybody has any questions? No? No questions online?
We haven't got any in the chat, but I can ask a quick one. I guess this is way outside of my area, so sorry if this is a silly question, but you said there was a big difference in the clouds going from 1D to 2D. Like, what happens if you go to 3D? Do you expect that to make a big difference?
Yeah, so it's interesting. On this planet, it really depends on, so the dominant flow in this atmosphere is really along this equatorial jet. You see some interesting flow near the poles, but it's not really where most of the mass is being transported significantly. So for these planets that may not, I mean, 3D, I think, in general will be important, and the only reason I haven't done that yet here is for computational difficulties. So we want to get rid of the initial conditions that we see in these models, so you have to run them to resolution. But I think it's less important in the case where you have the super rotating equatorial jet. But in the case where something like magnetic drag is really important, or in the case of a terrestrial planet where you expect to have this day side to night side flow, in that case you really do need to think more about 3D.
Okay, great, thank you. Super cool stuff.
All right, can we thank Diana again, everybody? Next up is Lewis.
How do I do things? Oh, thank you. There. I'll let you. You're the expert. Okay. Thank you. I assume you can all hear me, right? Cool. So thank you very much to the organizers and to the leads. My name is Luis Wellbanks, and I want to talk to you about some of the things that we're doing to look into JWST spectra, both in emission and transmission. Last year, I talked to you about some of the model advancements that we can do to characterize smaller rocky planets and how we can start talking about ultra-hot Jupiters that have inhomogeneities and how we can make models. Sorry, I cannot hear you. Take off the mic?
So turn it on.
Oh, okay. It's red. Cool. Oh, wow. Okay, that's interesting. Yeah, so last year I was talking about like how we can make multidimensional models, and we just heard Diana talk about multidimensional models, and I want to talk to you today about how can we make sure that we are working at the limits of our models and our data. Because any model advancement that we want to make sure that it is sustained by the data and that we're not overfitting, underfitting, and all that jazz. So I just wanted to make sure that we're all on the same page. There's planets. Planets go around stars. And when the planet goes in front of the star, some of the starlight goes past the atmosphere, and it gets an imprint of the chemical composition of the planet and its atmosphere. The observable of this is that, yes, it worked. Ultimately, we're looking at the apparent change of the planet size depending on the color that we're observing the planet. So, for example, in this case, we see that in the blue, sorry, there's no blue, in the yellow, the planet is the biggest, apparent color is the biggest, and therefore it blocks the most light. Whereas in the green, it is the smallest, and it is blocking less light from the star. This, as a grad student, I was like, this is just lies. And then I saw this very cool outreach plot from Vivian Parmentier and collaborators, former Sagan fellow. And this is the Earth and the Moon on the background. And I'm going to show you what this is in real color. But now we look at it at 8.6 microns, random color. And then we look at it at 9.6 microns. And like, if this was an eye test, I'm going to go back and forth, and you see that the Earth is getting bigger and it's blocking more light. Now, obviously, Earth didn't get bigger, but the apparent size of Earth changed. So we are really measuring this for other planets, planets outside of the solar system. And we know on Earth that this apparent change in size is because of ozone absorption in the atmosphere of Earth. So we could say, oh, we detected ozone on Earth. Cool. What do our observations look like? Well, we are effectively measuring the change. Come on, I feel like a Jedi. The change of the planet size as a function of color. So we see that here, the planet got bigger. Here, the planet got smaller. Obviously, by color, we talk about wavelengths. I'm showing you here between 3.6 and 5.2 microns, which is the wavelength range that PRISM is covering, near-spec PRISM on JWST. And this is the planet size, how much it blocked relative to the star. And I want to go back to the basics. And this is Sally Sue, future Hubble Fellow in 2040. She's an undergrad at our group. And she's doing the thing that I struggled as a baby, which was put the thing where it fits. And this is all we're doing as experts in transmission spectra. We're saying where the thing fits to match the observations. These are the cross-sections of the different molecules that we can measure here on Earth. There's laboratories, they shoot lasers, and they tell us how big the molecule seems to be as a function of color, as a function of wavelength. So these are observable, and we take that as a function of pressure and temperature. So then we compare this to the observations, and we do what Sally Sue does and see if it fits. So for example, this is the cross-section of methane, and here I'm showing you how it compares to the observations of WASP-39, and I hope you all are like, nah, it doesn't fit. So then you go to water, and like, maybe, sort of, could, but no, it doesn't fit. And then I'm going to show you CO2, if the computer cooperates, and then you're like, yeah, sure, it's better. There's things that don't fit, but it's better. And if you agree with me that this fits and that there's CO2 in WASP-39, congratulations, you just got a Nature paper, and NASA is going to do a big press release about you because you just found carbon dioxide for the first time in an exoplanet atmosphere. And this is what the JWST Early Release Science program did, with many of us being part of that collaboration. So this is how we can start finding things in exoplanet atmospheres. This has been done already with Hubble. This is, for example, a feature that many of us are now familiar with, which is a bump around 1.4 microns. And this is a water feature. And because of that, we have been able to find water in many, many exoplanets. But you see that the size and shapes of the features are very different. And here I'm also plotting you confidence intervals. And I'm going to get to you in a second about how we do that. Likewise, we've done this with sodium and potassium. But for example, I mean, we're inferring a potassium feature with like one tiny data point. I'm like, is that really potassium? Can we really say that there's potassium in this planet? And we do this with something called a retrieval. This is for historical reasons. Many of you have already talked about it in the cosmology and boom, things go boom sessions, which is an inference problem. You have a model, you compare it with the data, you do MCMC, nested sampling, something like that, and then you get your posterior distributions. For historical reasons, in exoplanets, we call it a retrieval, but it's a procedure to infer the atmospheric properties of an exoplanet from a set of observations. And we have to run a large ensemble of models. We are effectively doing a model comparison exercise. At the end of the day, a retrieval is the art of model comparison. We're comparing models with water and models without water, and we say which one fits the data better. We're comparing cloudy models versus cloud-free models, and we're saying which one fits the data better. And we're getting to the point where we're comparing 1D models versus 2D models versus 3D models with different inhomogeneities, and we're trying to see which one fits the data better. But this whole thing about which fits the data better is based on our metrics. And we sometimes call this a detection. Like I just showed you, we detect CO2. But I want to be very careful. We're not detecting CO2. We are detecting a preference for a model that has CO2. And we do this with chi-squares, with p-values, with BIC, with Bayesian evidence, and each one of these metrics, as all of you know, have their downfalls. So we can fall into the trap of comparing two equally bad models, because the true model of nature of what an exoplanet is far out. We don't know what it is. So we're at the risk of, at some point, claiming that a planet is giving us this little feature of 3D-ness when it could be the data that is giving us the real result of what we want. We are at the point where we could see in the daily Retrieval newspaper that astronomers find the 6 sigma detection of cheese on the moon. But it is really because we're comparing two wrong models. We're comparing the model that the moon is made out of cheese and the moon is made out of sponge. So if we have two equally bad models, we are at the point where we could be saying this. And we have said this type of things, and that is dangerous. So current model comparison metrics are giving us a single value. They just tell us your chi-squared is blah. And they're not telling us where our model is performing well and where our model is not performing well. And we can look back into the data side of things and be like, can I really trust this data point? And one of the things that I've been working for the last year with a dear friend of mine and collaborator, Peter McGill at Santa Cruz, is to use Bayesian leave-and-out cross-validation of exoplanet retrievals. So what this means is that we're going to get a score per data point that tells us how well the data is being fit by the model. It's giving us a prediction. And what we're going to be doing is that we are effectively removing one data point at a time and doing the inference problem again, and seeing how each data point is changing our posteriors and how each data point is changing our detection significances. This, in comparison to just regular retrievals, this is not prior sensitive, which is an issue for sometimes our abundances. What should be the prior for something that we don't understand? And using this method in Retrieval, tells us which data points are driving our inferences, which points are telling us that a physical species is being detected. I want to show you, for example, to build intuition at this point, I hope I convince you that there's a bump here, and a bump here. This is sodium, this is potassium, and this is water. So if I was to tell you which data points are driving the water feature, the water detection, well, I hope you would say that it would be the one around 1.4 microns. And this model that we're using colors the data points by their importance into driving our inference. The redder the data point, the more important it is on giving us significance for water, and the bluer the data point is not necessarily needed to give an inference of water. We've done this for hot Jupiter, had P41, which is controversial because there was a possibility of H- in the atmosphere. H- means that the atmosphere is ionizing, and that would be at very hot temperatures, but they found temperatures of about 1,000 Kelvin, where this should not be happening. And these observations are exquisite. I love these observations because they have a wide wavelength range, and they're basically telling us what we're going to be getting with JWST, and we're getting with JWST in terms of the number of data points. These ones cover the UV to the infrared. And they find the presence of the significant H- opacity provides a robust explanation to the observation, and they have a almost 3 sigma detection of H-. And the reason why they say that is, well, H- has this kind of bump. So they said, well, yeah, sure, water is coming down, so this is what is causing the H- detection. So we decided to test this on this data set, and we found that it's one particular data point that is driving this detection of H-. We use the same model, and we find that the particular 2.7 sigma detection of H- goes away if you just remove one data point. So now imagine if that data point was the one that was telling us that there's life on another planet. If the future inference that we're going to be making depends on a single data point. Before, with chi-squareds and p-values and all that stuff, we don't know where our model is failing. But with this type of metrics, we can go back and say, hey, is this data point really there? Did you not underestimate, overestimate? And actually, as it so happens, another team did a read reduction of these data points, and they change. And if we use those data points, there is no H-. This new metric is telling us that the detection of H- in HAD P41 depends on a single point. This is information that we did not have previously with previous metrics. This metric is not telling us that the detection of H- in HAD P41 is false. It could be there, I don't know. But then we are able to place context into our inferences. The thing that I would like to see moving forward is that you can use whatever model you want, and you can claim whatever detection you want, but the thing is, this is true if this part of my data is correct, if I can really trust this. And we can contextualize what we know and what we don't know about exoplanets. And this is one way in which we are going to be able to maximize the science output of JWST, because we've been waiting for these data for 20 years or more, and we want to make sure that whatever we say is robust, that we squeeze as much juice out of this, but we are not overreaching, and that we can contextualize our models correctly. So we want to make robust and reliable inferences so that we can maximize the science output. And to do so, we need to know the limits of our model, which is a lot what we're doing with making more complex models, but we want to also make sure that we have the limits of our data. Retrievals, or inferences, are at their core a model comparison exercise. And because we don't have the true model of planets, we want to be careful about what we do with these models. And what we're proposing is to implement Bayesian leave-one-out cross-validations that give us information about the per data point score of our inferences. And that way we know where we're working well, where we're working not so well, and we can go back and loop over this. Thank you very much.
Does anybody have any questions?
Hey, awesome talk. I was wondering with like JWST data, especially now that we're getting a ton of data, whether you've looked at how this metric changes if you like bin data versus leave it at like native resolution or something, and whether that causes a big difference in like the significance you get on what points are driving things.
That is one great thing that we can do with this. So here I'm currently showing at the per data point level leave one out, but in principle, we can leave n out. So one cool thing that I'm working on is that let's leave the n points that are in a bin, and then when you bin it down, you have one point that encompasses all that bin. So is the inference really the same? And are we really getting little information at the substructure level? And the cool thing about this is that from this, you can also make predictions about what you should be getting. So if you have current HST data with certain bins, if you were to propose for JWST data, how will that new data, how is that predicted by your current inference? Are they really matching? And what can you really get from the bins of that to get your JWST inferences to be the most informative for whatever science case you want to really put forward? So that is a great question, and that's something that's why we're developing this too. Thank you.
Any other questions? Okay. I don't know how to read.
We do have one in the chat. Would you like to go ahead and ask that?
Yes.
I can read it out. Sorry. So it says, Lewis, exciting work. I wonder how long does the validation process usually take? It seems repeating retrievals over the number of data points could be computationally expensive.
Absolutely, and that is the key point here. So the naive way of doing it, CJ is absolutely correct, is that you do n retrievals where you remove one data point at a time. But what we're introducing is to doing from a single retrieval. So there is no more additional cost. We're using importance sampling, which allows us to get that information from the already done retrieval. So there is no additional cost. And the good thing is that we can do this for any retrieval that has already been run in the past. We can apply this retroactively to see how that inferences was being informed by the data at that point. So no more time is the same time as one single retrieval.
All right. One quick question.
But you do have a data point there. What about not leaving it out entirely, but just enlarging the error bars or making it an upper limit or a lower limit or something like that?
Absolutely. That is something that we have already been doing, just like do error inflation. So then at that point, that becomes a model assumption. And then we can test whether this model assumption of inflating the error bars is actually going to be affecting our inferences. So now we're marginalizing over the model assumptions, including inflating the error bars, and marginalizing over data, if that makes sense.
All right. Well, thank Lewis again.
Thank you.
Next, we have up Megan.
There it is.
I think I can get it. Yeah, thank you. Are we still sharing? Yeah, we are. Okay. Okay. All right. I think my microphone's turned on. Yeah. All right. Cool. So hi, I'm Megan Mansfield. I'm at University of Arizona. And today I'm going to be telling you all about a precise measurement of the carbon to oxygen ratio in the ultra-hot Jupiter WASP-76b. So first, I kind of just wanted to motivate why we're interested in studying the abundances of these different gases in exoplanet atmospheres, particularly hot Jupiter atmospheres, and in particular, why the C to O ratio is so interesting. So this plot is from the first paper to kind of lay out why the C to O ratio can be interesting for studying planet formation. The idea is that as a planet's forming in a protoplanetary disk, if it's closer into the star, the disk is going to be hotter, and then the further out you go, the cooler the disk gets. And so as you move out through the disk, different gases like water, CO2, CO will condense out of the gas phase and go into solid phase. So depending on where your planet forms and whether it's accreting mostly gas or whether that gas is polluted by a lot of solid particles can change the relative ratio of carbon and oxygen in the planet compared to what you would find in the star. So that's kind of why we're interested in studying this in exoplanets. So unfortunately, up until now, most planets that we've looked at don't have really solid measurements for the C to O ratio or many abundances of different molecules. That's because they've mostly been studied so far at a low resolution with a small wavelength coverage. So here I'm just showing one instrument, the Wide Field Camera 3 on the Hubble Space Telescope, which is kind of the most widely used instrument at this point to study exoplanet atmospheres. It has a resolution of about 50 and covers a wavelength range from 1.1 to 1.7 microns, which for exoplanets means that you can essentially just measure a single broad absorption band of water. So today, instead, I'm going to be talking about some observations I took with the IGRINS spectrograph on the Gemini South Telescope. So IGRINS covers a slightly wider wavelength range from 1.5 to 2.5 microns, which means that it covers absorption features of a bunch of different molecules: water, CH4, CO, OH, essentially everything that we think would be a primary carrier of carbon or oxygen in these planets' atmospheres. And it's also at a much higher resolution of 45,000. So instead of measuring just a single broad absorption band, we can actually resolve individual absorption lines for each of those species. So that can give us a much better handle on the composition of the planet's atmosphere. So I'm currently leading a survey to measure transmission spectra of 11 different exoplanets with this IGRINS instrument. And our primary goal in this survey is to look for trends in their abundances and C/O ratios with planetary parameters like mass and temperature. And then we'll also combine this data set with other existing data sets for planets, for these planets from Hubble and Spitzer and other sources, to get kind of a fuller picture of what's going on in their atmospheres. So today I'm just going to be talking about one planet from this survey. There we go, WASP-76b, which is an ultra-hot Jupiter you can see up here with a temperature of about 2100 degrees. So we observed a single transit of this planet in October. And here I'm just showing our signal to noise per pair of AB exposures. We got a really good signal to noise for this planet, except for a couple orders on the edges of the throughput, which we just removed. And then in order to kind of process these data and get the planet signal out of this, we applied a principal component analysis, which I'm going to kind of explain why we do that and how that works. So our goal is we want to detect this planet, and we want to see the absorption features that we get as this planet transits in front of our star. And as the planet's transiting in front of its star, its features are going to be Doppler shifted because it's orbiting around the star. So the wavelength of all of the absorption features is going to be changing throughout the observation. Unfortunately, this planet is completely overwhelmed by the signals that we're getting from the star itself, from tellurics, and from the instrument throughput. And so when we actually look at our raw data, we don't see at all the planet signal. It's just hidden in the noise. But luckily, everything except the planet is pretty stationary with time, and the planet's the only thing that's significantly Doppler shifting. So we can separate out this planet using a principal component analysis, or PCA. If you've never done one of these before, it essentially identifies directions in your data along which most of the data points lie. So this is just one example over here showing some fake data for if you were measuring heights and widths of different fish. So you might get these red data points here. And if you apply a principal component analysis, this blue line running through here would be the first component it identifies. So from identifying that in your data, you could say, oh, all of my fish are different sizes, but their heights and widths scale relative to each other. So maybe I'm looking at the same species, just a bunch of fish at different ages. So we're doing essentially the same thing in our data, but the common components that we're able to identify are all of those non-planet features. So if we look at our raw data here, we can see these arc shapes are due to the instrument throughput. We can see some absorption lines from the star. This forest of lines over here is tellurics. And then if we take a single point and look at it in phase or time throughout the night, we essentially see an air mass trend. And then on the right here, I'm showing how these data look as we apply this PCA to clean out all of those components. So as we apply progressively more components, you can see that all of these different systematics get removed, and at the end, we're just left with the planetary signal. So then we can cross-correlate this signal with a model template to see what we're able to detect in the atmosphere of the planet. So here I'm showing that cross-correlation in radial velocity on the x-axis and phase or time during the observation on the y-axis. Whoops. Yeah, there we go. And these white lines here are showing the beginning and the end of the transit. So you can actually see two peaks in the cross-correlation here. The one I've highlighted in red here is from the planet because that's changing in radial velocity because of that Doppler shift. And then you can also see this mostly straight up and down line, which is actually some residual leftover from the star. So the other way that we can show this is this plot that's often referred to as a blob plot. We're great at naming things. Where basically what we're doing is taking all of this smeared out signal from the planet and condensing it all into one point that's defined in terms of the systemic velocity and the Keplerian orbital velocity of the star. And the white lines on that plot on the right show the expected values from the literature for this planet. So you can see we get this strong peak in our detection significance right near where we expect it, which is how we know we've detected the atmosphere of this planet. So we can do this with a bunch of models containing only single gases to kind of see what gases we're able to see in this planet's atmosphere. So for this planet, we were able to detect water, CO, and OH in its atmosphere. And then we searched for a bunch of other molecules. I'm showing some of them here, which are thought to exist in hot Jupiter atmospheres or have been detected before. But those were really only the 3 solid detections that we got. All right, so now that we've detected these molecules, what we really want to do is constrain their abundances so that we can say something about the C to O ratio in this planet's atmosphere. So I'm not going to go into detail about how we do this now because it's kind of complicated, but we did an atmospheric retrieval on these data. And this is some initial results from a very simple retrieval where we've got, you can see very nicely constrained abundances of all 3 of these gases. And that suggests that this planet has a metallicity about consistent with stellar, but a very superstellar C to O ratio of about 0.96. So this really high C to O ratio was actually quite a surprise to us. So we kind of looked into a little more whether this is driven by some assumptions we're making in our model or whether this is actually what's going on in the planet's atmosphere. So here I'm showing the abundances of those 3 gases that we were able to measure, COOH and water, compared to these lines in the background are predictions from a chemical equilibrium model for a planet at stellar metallicity and C to O ratio. And you can see that the CO and OH are pretty similar to what we would expect for this planet if it was a stellar composition, but the water abundance appears depleted compared to our expectations. However, you can also see that in this chemical equilibrium model, as you go up in the atmosphere, the abundance of these various oxygen-bearing molecules changes significantly. And that's because as you go into the upper layers of the atmosphere in this planet, the atmosphere gets quite a lot hotter, and so water starts to dissociate into OH and oxygen atoms. And so it's possible that there isn't actually water depletion in this planet's atmosphere, and what we're measuring, in fact, is some sort of average of these different regions of the planet's atmosphere that have different water abundances. So we're currently working on kind of upgrading this retrieval process to allow for things like non-constant abundances with altitude to try and look further into what's going on with this C to O ratio measurement. So this is just the first result from this survey, but we've observed a total of 5 planets so far. It's continuing for another year as well. So hopefully soon we'll have some more interesting results to share and possibly be able to make some intercomparisons between some of the planets in this data set. So before I end, I just wanted to say that I really, really wanted to be able to give a talk on JWST today. What I do in the other half of my life that's not high-res is JWST exoplanet stuff. But this talk is just about a month too early, and a lot of the really interesting results are still under embargo. So instead, I'm just going to give you a sneak peek of what you can expect, hopefully, in my talk next year. So here I'm actually just showing, this is some raw exoplanet data from the Spitzer Space Telescope. So everything you can see here is primarily just trends from the instrument. This is the actual transit of the planet in the middle, and these are eclipses here on the edges. This is considered a very good data set because you can actually see the planet without doing anything to the data to start with. So this is kind of what we had in the early days of exoplanet observations. So then next, a lot of exoplanet observations were taken with Hubble. Here again is a raw data set with Hubble. And again, you can see a transit right here in the middle, and then everything else you're seeing is just systematics from the telescope. So now, this is a raw data set that I've been working on the past couple months with JWST. I have not corrected these data for anything. This is straight out of the telescope what it looks like. So I'm really excited for what the next year is going to bring with these exoplanet observations with JWST, and I hope you'll be able to anticipate some very cool results in a talk next year. So just to conclude, we detected water, CO, and OH in WASP-76b with IGRINs.
Our initial retrieval results indicate that it has a metallicity consistent with stellar, but a significantly superstellar C/O ratio. But we're doing some ongoing work to kind of upgrade our models for this planet to look at things like a non-isothermal temperature profile, a varying abundance of altitude, as well as looking at things like whether we can see any limb differences between the two limbs that are observed in transit. And this is just the first result from this survey, so I'm very excited to see what this survey will bring us in the future. So before I end, I just wanted to say thanks to all my collaborators and to the NHFP leads and everyone who organized this conference for putting this all together for us. And I'd be happy to take any questions.
Hey, Megan, does anybody have any questions? Any questions online?
Simple question. I'm just wondering that amazing JWST light curve there. Like what percentage change is that?
What percentage you mean in? Like the dip in the flux there.
Yeah. Vaguely.
I took the maybe a couple percent. Who else is on this team? Who knows how? Yeah. So this is a planet that's been observed with HST before. This is actually the data that were in that first look paper. This is WASP-39 as well, with a different instrument, which is why I've stripped all the bars off it, so you can't tell what it is. But yeah, I think it's like 1% or 2%, maybe. Yeah.
So any other questions? Okay.
Very cool. I might have missed something. Did you say, okay, so when you're claiming that the carbon to oxygen is supersolar, did you say that you derive the carbon and oxygen from the host star?
Yeah, so the host star is essentially consistent with like solar-like, with big error bars, but yeah.
Okay, yeah, see, this is why I asked. So are you saying that it is solar, the carbon and oxygen, or was that re-derived?
The carbon and oxygen in the star, WASP-76, are close to solar, I believe. The carbon and oxygen that we actually measured in the planet are, yeah, basically like what we were measuring was a CO abundance that is like, consistent with what we'd expect if it was the same composition as the star WASP-76 and a depleted water abundance. So like the C/O ratio in the planet seems higher than the star. Yeah, if that makes sense. Does that answer your question?
Not sure. Sorry, because you said it's close to solar. I guess I'm still just wondering if the carbon and oxygen was re-derived for the host. And why I ask, this is well motivated, I promise, because there was a reanalysis of WASP-77 where there was a claim where either the carbon and oxygen was supersolar or subsolar, whatever it was, but they were doing it relative to the sun and not the actual host star. And then there's a reanalysis where they found it was kind of the opposite. So that's why I was asking.
Yeah, so these values are quoted relative to the host star, but the measurements of carbon and oxygen on the host star are not like, super precise, I think. Well, they're very precise for exoplanets. They're not very precise for probably anybody else. Yeah.
All right, thank you.
That answers your question.
All right, let's thank Megan again. So next up we have Ryan.
You can tell I'm not very good at using Macs. Where? Aha. Okay. Right, okay. So, hello everyone, I'm Ryan Macdonald. I'm a new incoming Sagan Fellow at the University of Michigan as of about 2 weeks ago. And so what I'm going to be talking about will be kind of linking and unifying together much of what we've just heard in the last few talks. So we've already heard from Diana about the importance of planets being multidimensional objects that vary all throughout their atmosphere. We heard from Luis about retrieval and inference frameworks. And just from Megan, we just saw about the incredible increase in the quality of data that we have with the JWST. So I'm going to be talking about a new technique I've been developing to use this much more precise data that we're now just getting to actually measure and infer the multidimensional properties of exoplanet atmospheres. So here is a schematic of an exoplanet transit, as we've seen a number of times in the previous talks. The essential key idea being that the effective area of the atmosphere changes with wavelength, primarily due to the absorption of different chemical species in the atmosphere, such as carbon dioxide, methane, water, etc., as we see there. So there's a lot of rich information contained in a transmission spectra. If we have very precise observations, we don't just identify what the chemical species are, but we can measure how abundant they are, we can measure the temperature field in the planet, and properties of clouds and aerosols. So when it comes to trying to explain a set of observations of an exoplanet atmosphere, there's two broad techniques that we tend to follow. The first kind of classical technique is called forward modeling. Essentially, we start from the basics, from the laws of physics and chemistry as we understand them. So things like hydrostatic equilibrium, the ideal gas law, understanding how gravity works. We churn forward all of the equations, and we produce a predicted model spectrum of the exoplanet's atmosphere. And this is incredibly important because ultimately it's forward models that enable us to get telescope time. They're our first prediction of what we expect to see. If you then get awarded your time by the TAC and get the observations, if the universe happens to be smiling on you, your model might actually match the observations. But herein comes a problem. Because how do you know that the one model that you happen to concoct is the only explanation for the set of observations, and there's not a family of models that could explain it with different molecules or a different temperature structure? And this is where the inverse problem comes in, that we also call atmospheric retrieval. Essentially, a retrieval just produces many tens of thousands to millions of models to map out the parameter space and give you statistical constraints on the various properties of the atmosphere. And that ultimately is what leads to papers like the carbon dioxide detection that we saw earlier. But there's a lot of assumptions going on inside this black box. It's not just magic. We have to make assumptions. And the key assumption that I'm going to be focusing on today is a common assumption that the atmosphere is one-dimensional. And what I mean by that is from complicated three-dimensional general circulation models, as shown in this animation on the left, we expect for highly irradiated hot Jupiters that the temperature distribution will be highly non-uniform. We have this tidally locked permanent day side, permanent night side, with a temperature gradient of over 1,000 degrees between each side. But we also see inhomogeneities, both on the night side and on the day side. So clearly this is a non-spherical object with a lot of complexity going on inside the atmosphere. But for computational convenience, when we want to make millions of models, the classic assumption has been to assume that the only direction where properties change is in the radial direction. So things like the chemical composition and the temperature only vary with altitude. So if we want to improve the inference problem to be able to, for example, measure the temperature differences, then we need to find a way to efficiently compute two-dimensional or three-dimensional models. And so this is something I've been working on for the last few years, and just in the last year we introduced kind of the first solution to this problem, a new technique that we came up with that we call Trident, because we love acronyms. Essentially, it's just a clever coordinate system choice that allows you to express the three-dimensional radiative transfer problem as a rather succinct equation using a tensor dot product. The details don't matter so much, but essentially what's going on is that from the observer's perspective, you'll see differences in the effective size between the morning and evening side of the planet. So you shoot rays through each of a set of angles from the observer's perspective, and then each ray comes through the day side and passes out through the night side, encountering different regions with different temperatures, cloud properties, and chemical compositions. And by expressing it in terms of a linear algebra operation, it's then very efficient using standard linear algebra packages to compute a three-dimensional spectrum in less than a second, which is great, because then using multiple cores, you can easily compute hundreds of thousands of three-dimensional models. So that was half the battle, but the other problem is, how do you parametrically describe three-dimensional models? Because if you, for example, had as parameters, what is the water abundance at every single longitude and latitude, what is the same for the carbon dioxide abundance, then very quickly you've got hundreds of free parameters and you'll never be able to actually fit the observations. So the second key thing that I've been working on is simplified models to be able to describe parametrically to first order three-dimensional structures in temperature, chemical composition, and cloud properties. So, for example, this is a two-scale visualization of a four-parameter model that we came up with to describe how the temperature distribution varies in 3 dimensions. And you can see on the right there that it can capture this day-side to night-side temperature difference, but also inhomogeneities between the evening and morning terminators from the observer's perspective. If we combine these two slices together, then in 3 dimensions, this is what the parameterization looks like. So you can see that it's capturing some of the first-order complexity from these 3-dimensional general circulation models. And this is to scale. So if you look at the wire mesh around it, which is a sphere with the radius of the maximum extent of the day side, you can clearly see how non-spherical this planet is. So this model captures the geometric effect of the 3-dimensional information when rays pass through this non-spherical object as well. As we heard from Diana as well earlier, clouds and aerosols in these atmospheres, we also expect them not to be uniformly distributed. They can be localized at certain longitudes and latitudes. So we came up with a simplified cloud model that we call the iceberg cloud model, which is essentially a slab of cloud localized in a particular region of the atmosphere, which allows you to tease out from the spectrum where in the atmosphere the cloud actually is. So 2 key takeaways that we found in terms of how can you distinguish from just looking at a spectrum whether a planet is 1D, 2D, or 3D. Qualitatively, there's 2 key trends that we noticed. So the first is if you have a change in the abundance of an absorbing molecule between the day side and the night side, such as water absorption shown in the top panels here, the key change is that the relative amplitudes of some of the absorption features change as the amount of water varies along the line of sight. And the magnitude of this change is much above the expected noise floor from the JWST, so this is eminently detectable. And the second change, if you rotate the planet around by 90 degrees and look at differences between the 2 different sides of the planet, this is a little bit more subtle, this change. It's got a lower magnitude than day-night changes. But effectively what happens is the peak of absorption features changes by a different amount to the wings of the absorption features. And so this kind of skews the wing shape. So these 2 distinct qualitative changes combined allow you to infer the 2 different types of 2-dimensionality between the day side and the night side and between the morning and evening terminators. So by combining these 2 effects, we can measure 3-dimensional properties of the atmospheres from their spectra. So what I've been working on at the moment, and I will be working on throughout my Sagan Fellowship, is now then taking this 3-dimensional model and then applying it to real observations to try and statistically identify these multidimensional properties. And so for that, Trident was a tool that we combined, equipped by our code Poseidon, and we give you a brief preview. So here is a flowchart illustrating how the Poseidon code actually works. Essentially, all of this is just showing that the 3-dimensional model I was showing earlier is repeatedly called, compared to a set of observations, And then depending on how far off the observations it is by computing the likelihood function, you can use an MCMC or nested sampling code to map out the parameter space and give you both a posterior distribution and statistical significances for the various model components. So here is a set of simulated observations from JWST for an ultra-hot Jupiter for a program that we're expecting to get next year. And for this particular simulation, we assumed a day-side to night-side temperature difference with water dissociation. So there is less water on the day side than the night side because of high-energy photons dissociating water molecules. And by running a retrieval on this simulated data set, you can statistically infer that there is a different temperature profile on the day side and the night side. And for example, on this corner plot, this parameter here is encoding the difference in temperature between the day side and the night side. So you can statistically measure that there is a 2000 Kelvin difference in temperature between the day side and the night side. And you can also infer whether the day side or the night side has more water. So you can tell what the chemical processes are that is leading to particular regions having more or less of a given molecule. And the second application that I'll show here is for a cooler planet, a Neptune-like planet. So for these planets, some of the main inhomogeneities can come between the two different sides of the terminators. Even a change of a couple hundred degrees between the two sides can cause you to cross over between two different chemical regimes. In this particular case, on one side of the planet, most of the carbon can be locked up in carbon dioxide, while on the other side, it is locked up in methane. And this is just showing that you can identify which side of the planet has more methane than the other. And you can also place measurements on the cloud properties. So that second parameter there is the fraction of the terminator covered with clouds. So you can measure that the atmosphere isn't completely covered by clouds, and hence place some statistical constraints on models like the ones we saw from Diana earlier. With that, I will leave up my conclusions, and I'll be happy to take any questions.
Thank you. Do we have any questions? Any questions online? Okay, well, if there's not any questions, Ryan will be here if you have other questions later. The next talk is, I believe, online. Are you here?
Can you see my screen?
Okay, now you can try to share, CJ.
Okay. Let me see. Okay, can you see the screen?
Yes, we can see it now.
Hello?
Looks good.
Okay.
Looks good. Take it away.
Thank you. All right. Okay. Hello, everyone. I'm ZJ, and I will be starting my position at UC Santa Cruz at the beginning of the next month. And first, I would like to thank the organizers to make this hybrid meeting happen. At first, I would like to briefly introduce my research interests. And I have a pretty broad kind of passion about the evolution and formation of the brown dwarfs and exoplanets. And there have been several things going on in my plate recently. First of that is that I've been leading a survey to search for giant planets and brown dwarfs that are wide orbit companions to stars. And then try to collect their spectra and model their atmospheres. The second one is that I've been studying the atmospheric escape of irradiated planets. And specifically, we have discovered some helium outflow from hot Jupiter. And the third one is we are also interested in studying the architecture of the stellar binaries and try to understand the stellar multiplicity on the formation and the properties of their planets. So for today's talk, I would like to focus on the first one, And I would like to make the point that the wide orbit brown dwarf companions are really valuable benchmarks to help us to reliably characterize the properties of image planets and try to understand how they form. So at first, I think everyone must have been really excited over the past few weeks about some new and fresh data and science that are enabled by the James Webb data. And personally, for me, I'm really impressed by this observation for this exoplanet, HIP 65426b, and this study led by Aaron Carter and the ERS team. And at the bottom, we can see the planet really clearly in different wavelengths, mostly in the mid-infrared, and they are taken by the James Webb using 2 instruments. And thanks to these kind of new measurements of the planet fluxes, now the SED of the planet is really extended to the longer wavelengths. If we take a look at the top panel, the black symbols mark the previously observed spectrophotometry for this planet, while the orange ones are the new fluxes from the James Webb. And we can see there's some even fluxes measured beyond 10 micron. At the bottom, there's another object or amazing brown dwarf, VHS 1256b, also from the ERS team, led by Brittany Miles. And we can see this high quality spectra combining NIRSPEC and MIRI, and the spectra extend from 1 to 20 micron. And most of the spectral features have never been seen before from the ground. So now, given this kind of rich data set, combining both of the existing ground-based data and also this kind of high-quality, mind-blowing spectra from the James Webb, I think we're really at the position that we can move forward to characterize the spectra and understand how the planet forms. And as we know, like in the recent years, one of the emerging kind of candidates for studying the planet formation is to study the elemental abundance ratios. And one of that could be the C2O ratio. And here at the bottom, we show the expected C2O ratio as a function of the orbital separation in the circumstantial disk. And we can see that the metric of the C2O is really kind of footprint about the different planet formation modes and also the location, the formation site of the planet in the disk. So while this is really exciting theoretically, there are also some really great progress from the observations that are trying to measure the C2O ratios. So here I'm showing a non-exhaustive list of the measured C2O ratio for the image planets and brown dwarfs. As I know, there are more kind of measurements for the closer in planets, as what Megan has just presented. And orange, the image planets, and blue ones are the brown dwarfs. So we can see there are several objects that are being measured and also a group of brown dwarfs that are free floating in the field. But overall, we're definitely still at the early stage to collect for more elemental abundance ratios for all of these interesting objects. And I personally, for the next few years, would like to contribute to these measurements as well, based on the talk that I will be giving soon. And all of these are really exciting, but in the meanwhile, as we are trying to interpret this C2O ratio and extrapolate that to the planet formation pathways, one of the things that we have to keep in mind is that most of these elemental abundance ratios are model dependent. But in the meanwhile, the model predictions can bear systematic uncertainties. So if we take a look at on the right, there are just so many physical and chemical processes that are going on in the atmospheres of the planets. And the modelers are trying really hard to squeeze all of this into the models to be few free parameters. And this is for the grid models. And then at the end of the day, the model predictions will be mostly dependent on the certain assumptions that are made in the models. And therefore, the predictions are not necessarily always consistent with the true values, if we know that. So here are two quick examples. At the bottom on the left, this is a study of the image planet, Fit1 Area B. Both top and bottom panels show the observed emission spectra in grid points. And the red lines are the best fitted models with different assumptions. So the top one has the assumption of solar abundance and cloudless atmospheres, and the bottom one has assumed a non-solar abundance and cloudy atmospheres. So while we can see that both these kind of red lines or the models can fit the spectral photometry pretty well, but the predictions from these two types of models are very different, especially the effective temperature and surface gravity. So we could probably be puzzled that and try to see like which set of predictions are more reliable, and if they're not, then what are the quantitative systematic uncertainties of these predictions. And on the right, there's another example from my recent study of a large population of the late dwarfs. And for this, we are trying to compare the spectra for all of these 55 objects to the state-of-the-art model atmospheres. And that is from the Small Bobcat, which assume the atmospheres is cloudless. And the spectroscopically inferred iron abundance of these late dwarfs from our work is shown in blue histogram. And when we compare this iron abundance of the late dwarfs to the local content of the solar neighborhood, what we see is that there's a kind of large difference, as large as 0.4 dex. And through more detailed analysis, we believe most of this difference is because the models can systematically underpredict the iron abundance for these objects. And all of these are saying that the models are nothing wrong, but just that when we use the models with a certain assumptions, we have to take care like whether the assumption can fit our objects well. And if they're not, then there could be some quantitative systematic errors that we want to understand. So quantifying the modeling systematics is definitely not a trivial work. And through my work or research, I would like to highlight that there's a promising candidate to calibrate the model predictions, and those are the brown dwarfs that are wide orbit companions to stars. And compared to the image exoplanets, the brown dwarfs, as we know, have operate very similar atmospheric processes as the planets, and they have really similar spectrophotometry and morphology. And in addition, thanks to the wide separation, these brown dwarfs can conveniently obtain high-quality spectra for us to do some detailed spectral analysis. And the most important reason that these brown dwarf companions can serve as a benchmark is because their properties can be independently inferred from their host stars. While for most of the free-floating brown dwarfs in the field, they do not have the host stars or any stars that they're associated with, and therefore their underlying properties are mostly unknown. And for this kind of wide companions, their ages and iron abundance, state-to ratio, and many others could be inferred from the host stars. And this is because, given this high mass and wide separation, it's very likely that these brown dwarfs have been formed in a similar way as the stellar binary components. And therefore, in order to use this kind of independent matter properties, the process is something like, at first, we obtain the spectra for these brown dwarfs, and then we do the typical data model comparison by either kind of retrieval analysis or formal modeling, as what Ryan has elaborated pretty well. And then what we got is, what we will get is a set of physical properties predicted from the models. But in the meanwhile, if we compare the model predictions to the expectations from the host stars, given the host star abundance and age and elemental abundance ratios, we'll be able to directly quantify what are the systematic errors in the certain parameters for a given object and model. So following this idea, I have been conducting a series of formal modeling analysis. And for today, I would like to show three quick examples. So all of these three objects are late dwarfs that are also co-moving together with a star. And therefore, they have the known age and abundances. And at the bottom, we are doing the formal modeling analysis using the Small Bobcat models. The black is the observed data.
2 minutes left.
Best fitted models. And for the data model comparison, we have been trying really hard, try to incorporate all of the possible kind of error budget in the process, including the correlated noise, modeling systematics, and also the model interpolation. And that will, like the whole process might worth another talk, but I will just go to the results right now. So in the color plot, what I'm showing is a delta parameter, and the delta is the difference between the model predictions for a given parameter and the ground truths that are predicted from expected from the host star. And therefore, this delta value is a quantification of the modeling systematics. So different colors mean different objects. So and also one thing I forgot to mention is that if the delta is consistent with 0, that means the model predictions are reliable, and if it's like positive or negative, that means the models can under or over predict certain parameters, of course. And for the first two objects, HD 3651b and JJ 571d, they have similar effective temperature and surface gravity. And what we see here is that the delta T of these two objects are pretty consistent with zero. That means the models for these two Leydig dwarfs are pretty reliable in predicting their temperature from the formal model analysis. But the surface gravity and metallicity for these two objects are greatly underestimated by 1.3 DAX and 0.3 DAX respectively. But when we go to the third object, Ross 450C, which has the lowest temperature and lowest log G, we see the case is very different. So the models can over-predict the effective temperature by 120K, but the model-dependent log G and metallicity are pretty consistent with that from Poseidon. So using these three objects, we seem to see a trend that the model physics seems to be a function of the object's path and log G. So if we can expand this analysis to an even larger sample of the benchmarks, we'll be able to first verify the trend, and also if the trend is held, then we'll be able to derive the empirical calibration of the model predictions. And recently, I'm also working with an undergrad student who is now a graduate student in University of Oregon, and we are doing this kind of formal model analysis for even larger sample of the outward benchmarks. All of these are saying that it's really important to have a large sample of the benchmarks, and therefore I have been also doing a large-scale search for these benchmarks. So on the left, in the brown color, I'm showing the previous.
A minute over, by the way. So if you can wrap it up.
I will wrap up soon. So the orange are the previously known brown dwarf companions on the white orbits. In total, there are 40. And from the survey that I'm now leading, there are like around 40 more. And therefore, the sample has been greatly expanded. And in addition to my own work, there have been also a lot of contributions from my colleagues, especially those from the backyard works Planet 9. So far, this is the last slide. And so for the next few years, my goal is really try to uniformly characterize both the benchmarks and their host nodes. And the goal is to obtain the robust state-to ratio for both the planet and star and study the ratios of their state-to as a function of separation, try to better understand the formation modes of the planets across the disk. Thank you so much. I'm ready to take the question. I'm sorry for taking a long time.
All right, well, let's thank him again for the talk. We only have time for a very quick question. Anybody in the audience or online? Okay.
Hi, CJ. Thank you for your talk. We had some sound issues, so I didn't quite get it. If you were to order your model systematics, which one would you like to tackle first? Which one is the one that you need to get to your goal?
Yeah, so the first set of the models are from the Sonora. So there are Sonora Bobcat models that I've already tested. And also my collaborator, Caroline Morley, she is now doing the cloudy models for the Sonora. And I will try to incorporate the Sonora cloudy models to all of the benchmarks for the next step. And this is for the grid models. And for the retrieval, I'm also collaborating with Paul Mollier, and we are trying to calibrate the potato reference.
Okay, thank you. If there's any other questions, you can find them on Slack. Thank you for your talk again.
Right.
Next up is Martha. This is the last talk before the break.
Yeah. Oh, did it move back? Yeah. Okay, awesome. Okay, that's good. Okay, thanks. So I'm Marta Bryan. I'm currently, sorry? Oh, we're not sharing. Ah. Great. Yeah, so I'm Marta Bryan. I'm currently a Sagan Fellow at UC Berkeley, but starting in January, I'll be moving to the University of Toronto as an assistant faculty. So I thought it would be fun to use this time to share some highlights of what I accomplished during my postdoc, and also talk a bit about what I've been working on more recently. So, we found thousands of planets, huge diversity of systems. But for the vast majority of these planets, we typically only know a handful of their properties. Maybe we know their mass, if you got radial velocities, radius, maybe you know something about their orbit. And we've learned a lot from just mass, radius, orbit, but these alone are insufficient for getting fleshed out stories of formation histories. And so a promising strategy is to target planetary atmospheres because, oh, no, that is how you move forward, sorry. So a promising strategy is to target planetary atmospheres because if you're sensitive to their atmospheres, you can measure things like atmosphere compositions, how fast your planet is spinning. You can measure planetary obliquities, not stellar, but planetary. And all these properties are sensitive to a broad range of very open questions about how planets form and evolve. And the way that you can get all these properties on the left here is with high-resolution spectroscopy. So I've been targeting this population of directly imaged planets on the right there because this is one of the only population of objects that is currently accessible with high-resolution spectroscopy. So these things are super bright because they're younger and they're massive, and they're very far from their host stars, which means they're not going to be buried beneath the glare of their host stars. And so that means that you can extract spectra of the planets themselves. Now, this population of objects, I also think it's an especially interesting population of companions because their masses are right around the determined burning limit. And so it raises the question, did these objects form bottom-up via core accretion, which is where these cores are growing via the agglomeration of solids until they become massive enough to accrete a substantial gas atmosphere from the surrounding disk? So did these things form bottom-up like we think most, if not all these planets closer into their host stars did? Or did they form top-down via gravitational instability like a star and brown dwarf? And so one way that I decided to get at this question of how this population of objects formed is by measuring how fast they spin. So here is a cartoon figure showing you how we thought about how planetary spins evolve over time. So models suggest that no matter how a gas giant is forming, whether it's top-down via gravitational instability, bottom-up via core accretion, no matter how this planet is forming, a growing protoplanet should acquire as much angular momentum as the gas that it accretes. And after that accretion stops, disk is dispersed, this planet is going to cool and contract, which is going to cause it to spin up. Now, our naive expectation is, well, everyone should be spinning at breakup speed unless they're somehow able to shed that angular momentum. And so we can ask ourselves, okay, are planets spinning at breakup speed? If not, why not? What mechanism can extract angular momentum from these systems? Do planets lose angular momentum? Do they conserve it? What sets their initial spins? This was all pretty unexplored territory. And so to figure out what's going on here, starting in 2015, I led a survey using NIRSpec at Keck to measure rotational line broadening in near-infrared high-resolution spectra. And in 2020, I published a study with 27 planetary spin measurements, over half of which were from my survey. And here I'm plotting those 27 spin measurements as a function of radius, where these points are colored according to object age. So younger points darker points are younger objects, brighter points are older objects. And, you can see that smaller objects spinning more quickly. And this trend is a strong function of age. So as these objects are getting older, they're shrinking, spinning up. But, on top of that, the slope of this trend is consistent with conservation of angular momentum. V goes as 1 over r. And so the picture we're getting here is that when these planets are young, they're conserved angular momentum as they cool and contract as they spin up. So we understand the slope of this trend. Now we want to get a handle on its normalization. So what is setting the angular momentum budgets for planets? And so to get at that, here I'm plotting rotation rate as a fraction of breakup speed as a function of age, where these are all the same points as the previous figure. Solar system gas giants are in purple on the right there. Now, what you can see is that, top of the plot, that's breakup speed. All the points are down here, like order of magnitude below breakup. And while we already knew the solar system gas giants were spinning well below breakup, what we're finding is that planetary spins are set an order of magnitude below breakup, starting from when these planets are extremely young. So the youngest objects in our sample are in Taurus, so they're just a couple million years old. And so now the question is, all right, what mechanism can extract all that angular momentum from these systems, starting very early in a planet's lifetime? And so what we think is going on is that when these planets are young, they're generating strong magnetic fields, which couple with the surrounding ionized circumplanetary disk, and this coupling produces magnetic torques that can break and expel angular momentum from the system, which spins these planets down. Now, if you want to level up planetary spin measurements, you can try going after planetary obliquities, which is the angle between a planet's spin axis and its orbital plane. Or in other words, it's why the Earth has season, right? We have this 23-degree tilt as we're going around our sun. And so looking at our solar system plans, you can see huge range of orientations, right? Uranus is on its side, Venus is upside down, Saturn is tilted. And these orientations, they tell us stories of processes like collisions, accretion of planetesimals, secular spin resonances. But we want to know, what is going on with exoplanets. And so in 2020, I published the first planetary obliquity measurement outside the solar system, and last year we got the second one. So here I'm showing the images of these two systems we looked at. So on the left here, this is 2 mass 0122. On the right, this is HD 106906. Ignore this eye of Sauron, that is a mask. Both of these systems are naturally pretty young. They both have 10-ish Jupiter mass companions orbiting quite far away. So over here it's about 50 AU. Over there it's over 700 AU away. And in HD 106, you might see this asymmetric debris disk, which we know is oriented about edge on. Now, to measure an exoplanetary obliquity, you need to combine a few different observables. So to get the spin angular momentum vector of the planet, I measured V sin i's using high-resolution spectra, and I combined that with previously published photometric rotation periods. You put those together, you can constrain this spin angular momentum vector for the planet, and then to get this orbit normal, you need a fraction of the astrometric orbit. And again, it is the relative angle between those two angular momentum vectors that is this obliquity that we want. So here's what these two systems look like. These arrows are the angular momentum vectors that we've constrained for these systems. So over here, this is 2 mass 0122, we've got planet spin, stellar spin, orbit normal. In HD 106, we've got planet spin, orbit normal, disk normal, because we've got that debris disk. Now, there are some uncertainties on how these vectors are oriented, because we don't actually know how these spin vectors are oriented in the sky plane, because when you're combining V sin and rotation period, you're only constraining those vectors along your line of sight. But even with those uncertainties, there are some things that hold up. So for this system, we have what looks to be an aligned stellar obliquity. So stellar spin, orbit normal look pretty aligned, but a misaligned planet obliquity, right? That planet is tilted. And then in HD 106, everything is misaligned, but in particular, the planet spin, which is almost pole on, and the disk, which is edge on. And that is weird, right? Why is the planet spin so misaligned with its disk? And so for both of these systems, a promising scenario is one where these companions are forming top-down via gravitational instability. And so in this scenario, you have a disk that is so massive that its own self-gravity is driving turbulent motions. And these turbulent eddies of gas are going to be spinning in a variety of directions, and then they are going to collapse under their own self-gravity, naturally producing fragments that have a range of obliquities. And so this mechanism was recently demonstrated in Jennings and Chang, where here I'm showing a snapshot from their 3D simulation of a gravitroturbulent disk. And you can see this pancake of a fragment It's tilted. So it has got a high obliquity. And so this is the scenario that we're picturing for both of these systems. Okay, so planetary spins, obliquities, that's a lot of what I focused on during my postdoc. In the last couple of months, I switched gears a little bit to thinking about what can we learn about the formation histories of these young planets using their atmospheric compositions. And so the idea is, for any object forming in a disk, the reservoir material that planet is going to have to form and to grow is going to depend on where and when that planet forms in the disk. Because for one, these just have temperature gradients, radially, vertically. And so molecules are going to freeze out at different locations. And then these ice lines are going to evolve over time. Material drifts inwards over time. And so atmospheric compositions can tell you something about where and when these planets are forming. And I think probing these atmospheric compositions at high resolution is a promising avenue, because typical strategies using low resolution spectra can be limited by, clouds. We've heard about clouds. Clouds are everywhere. And modeling atmospheres at low resolution, there can be degeneracies between clouds and composition, and it can be hard to know if you got the composition right. But going to high resolution, you can bypass a lot of this because you're resolving these individual molecular features. And so you can directly constrain relative abundances of molecules by comparing ratios of observed line depths. So the experiment that I'm doing right now is I have 3 directly imaged objects. Everybody is in the same star-forming region, so similar formation conditions, similar ages. Everybody has a comparable spectral type, so similar masses. The main difference is that one is bounded and 2 are not. Now we know how these free-floating objects formed, right? These are brown dwarfs. They form top-down via gravitational stability in a molecular cloud. But the formation parameter space for this bound object, it's much more open. Did it form top-down, bottom-up, in a disk, not in a disk? And so you can imagine that maybe we might expect the 2 free-floating objects to have similar atmospheric compositions. And if we found that that was the case, and if this bound object had a different composition, that could point to a difference in formation history. This is my last slide. And so, right now I'm using high-resolution spectra for these 3 directly imaged objects with the open-source atmospheric retrieval code Petit Radtrans developed by Paul Mollier and others to constrain the atmospheric compositions of these 3 objects and to compare them to each other. And this is very much a work in progress, but just as a teaser, I wanted to show this corner plot showing constraints on C/O ratio and metallicity for these 3 objects. And so the 2 free-floating objects are purple and blue, bound object is in red. And so what you'll notice is that, everybody kind of has a similar C/O ratio, but the bound object seems to have a higher metallicity. And, there's certainly more model tests that I need to do before saying whether or not this is real, but if this holds up, it could point to this kind of comparison being an interesting way to probe the formation histories of these young planets. So I'm out of time, so I'll just leave this up, and I'm happy to take questions.
All right, let's thank Martha. Does anybody have any questions? Oops.
This is really cool. The metallicity for the bounded object, the red one.
Yes.
Is it consistent, or where does it stand with the expectations for the mass of the object?
Oh, I mean, these are all so these are all directly imaged objects, so their masses are like plus or minus 5 Jupiter masses or something. So these are all like 10, 20 Jupiter massage objects.
Yes.
Yeah.
Okay. Thank you.
Other questions from anybody? So I actually have a question about your spin measurements. So you said you can have some kind of idea about the magnetic field strength of these planets?
Yes.
You probably were expecting this question.
Yep.
What are the estimates that you're getting for these planets?
Yeah, so I mean, right now we're sort of assuming that the Christensen 2009 relation is sort of what we might expect. So 500 Gauss a kilogauss. And what I find comforting is some of the measurements of brown dwarfs that are being made through these radio aurora measurements, showing that for objects that are maybe a little bit more massive, you might expect to see some of these like huge magnetic fields when these things are extremely young.
Okay, thank you. We can talk more about that. Any other questions online? I think so. Any more? Oh, sorry.
We do have a question from ZJ in the chat.
Okay, so we have one question in person, and we can go online after that.
Okay.
Hi, really nice talk. I guess from a formation perspective, it's really interesting to be able to measure angular momentum, right? But how do you imagine being able to disentangle the angular momentum kind of flux process in this circumplanetary disk scenario versus something that happens through a more like dry interaction between bodies in the system? So like a scattering event, for example.
Oh, yeah. So you can certainly, so this is, so this sort of like tilting in a turbulent medium. That's not the only sort of scenario that we pictured. So, what's nice is that you don't just have like one angular momentum vector, you have three for these systems. And so you can say, okay, what combination of things can give you the misalignments that you'd expect? So, we could consider like a stellar flyby. We can consider what if these things were captured, there are a couple scenarios that could explain sort of all three misalignments. So this sort of turbulent medium is one. Capture could be another because you wouldn't necessarily expect alignment. This is for HD 106. You wouldn't necessarily expect alignment between any of the three vectors. But we've seen that, the presence of a disk can torque this orbit back into alignment. And so, maybe that might not be able to explain the misalignment we see between the disk and the orbit. But yeah, definitely for each of these individual systems, considering multiple scenarios, it's important, yeah.
And the question online?
ZJ, would you like to unmute and ask it yourself?
Yes. These are really cool results. I wonder if the data of those three planets shown here are from the same instrument and or like whether they have the same wavelengths and spectral resolution.
Yes. So these are all exactly the same wavelength range, exactly the same instrument. I think most were taken on the same night. So, yes.
Oh, wow. Okay.
Yeah, this is all NIRSpec. NIRSpec.
That's wonderful. Thanks.
Yeah.
All right, well, let's thank everybody for the session again. Announcements? Okay, come back at noon. Sounds good. Bye.
He'll cut your talk in this session,
okay.
So it won't be online later.
Okay.
You have to stream it. So.
Oh yeah, no, that's great. Thank you. I am running away with this, aren't I? Sorry. Oh yeah. Okay, yes.
No, he didn't mirror.
Yeah.
Maybe if we mirrored it would help.
No, we've had the problem.
Yeah.
I don't use that as a pointer. I don't know. We're just trying to make sure that everybody can see what's going on.
Yeah. Sorry, give me 1 second. Sorry, Andy.
So I think that they're not labeled. Two different populations like this way to be assessed. Especially since even though you would expect you would expect that to be one, but oh yes, so
Okay.
Wait, wait.
Yes, so we also see scatters. Oh, okay.
Fuck.
But it doesn't have to be months. Oh, so we won't be able to see it remotely. How about a little malware? Yes, yes, yes. When is it a brain? Yeah.
Okay, it says I've signed in. Google Drive. Okay. Let's see if it's actually working. Oh, it's a weird find there.
The last time it was the under.
Yeah, it would be over here. Oh, here it is, Google Drive. See? What? I don't know what you guys do to your... Why can't I just tap with my thing? There it goes. Why, how do I just open that? I don't know what's going on with your... I cannot handle your... There you go, presentations. And open with terminal. No, I just want to open it in the goddamn font. Excuse me. I just don't... What do you do with here? What did you do?
Just double click.
That's what I did. I don't know. Okay. Let's do it in the... This is hard to read.
You can close this.
No, that's not what I mean. Oh. I don't understand what's going on here with this, but... There's list. Okay. Can we put this out of dark mode and light mode? Let's see.
There's the preferences, yeah.
There's the preferences. Ah, there we go. I don't know what they've done to the Touch ID. Where is the, is it general?
Should we maybe display or?
Yeah, light. All right. Okay.
Thank you very much, Andy. Let me configure the.
I don't know what it is to. They have.
Oh, yeah, it's a new one. Sorry.
Yeah, no, I don't know. Or yeah, I just find it. I had these problems before with the track pads.
Yeah, let me join the meeting. Thank you. So, is it on? Would you rather have it mirrored, or would you like, is it okay to look? What do you prefer? Mirror, okay. 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 Okay, let me mirror. Yeah, it's mirrored right now. Yes, yes. Yes, yes. The only people, it's going to just affect the people at home. They won't see the tracker, but you can still forward your slides. Yes. Yeah, give me 1 second.
Test.
Who's first? What's the order? Okay, all right. Let me know where you. Which one? Oh, right at the bottom. Is it alphabetical order?
Yeah, there I am. Yeah.
Want to use keynote, right? This is it.
The bottom. That one. Yeah.
Okay.
Yeah.
Close some of these. Yes, I just want to close that. Can you? Let you know you can. Your rail is mute. It's on.
Okay.
Red is mute. Green is on.
So just put this.
Yeah, yeah. But if you're coming after her, yeah. So it will still be active, then she can just hand it to you. How are you, Katie? I had not seen you. Sorry?
I said, how many years?
Yeah, I've not seen you in yeah. But I guess I've seen you on video conference, the site up here, yeah. Mine's standing aside. I just want to make sure that nothing's being cut off. Yeah. And that's not your fault, it's them cutting it off. Okay, all right, but it looks fine on this side, yeah. The bottom, that 80 is being cut off, so I wanted to make sure it's not. Okay. Make sure it's really. Okay. So you are, tell me what the name of your slide.
HUI.
You're very first, right? So I guess I won't close it. I'll just minimize yours. You're HUI?
HUI.
Right here.
Yes.
Here. Right, you can just look here because the screens are mirrored. So just to let you know, it's taking a little while because it's the first time opening.
Sure. So maybe I also don't need to close it. Oh, wow.
No, it won't happen again. This is.
See, this one, right?
Yes. And of course, just. Oh. Let me see if it's sharing the right screen. Hold on.
Okay.
But not had a permanent office. I didn't think, I thought that was like, because there's not, like, because I thought all SCSA people have to be in either. Flyers?
I cannot.
So that was where my office.
No. I can do it by my by the keyboard, but cannot with this. Oh yeah, now I can. Yeah, I think that will do. Everything's good? Nice.
Thank you so much. She's first, right?
Yes, she's first.
What's her name, by the way? Catherine. Catherine? I'm sorry. So I can have your slides up?
Oh, perfect, yeah.
Okay.
Yeah, of course.
Oh, but you see, when I don't do dual screens, it puts the slides there.
I think it's more important that it's synced than the
Yeah, because I may need to do it up on this side so that we don't get that bar in the middle.
I'm so used to like my ergonomic like Miller at home. I know. That I like got home. And I woke up Tuesday morning. Not 20 anymore.
Sure. What time we start? Noon?
Yeah.
Yours is a keynote, right?
Yeah.
After that, we get. Can I see the schedule? It's up. It's you then. Then after him.
And then.
A remote.
Yeah, that's me.
Oh, okay.
And then how do I turn? I put the
Ready? Yes, yeah.
Two in person, two remote.
Yeah. Then the next two after these are all remote. After the local ones, it's in remote.
Yes. Yeah,
Okay.
yeah.
Okay. Let me. You right?
Yeah. Okay, last one. Always looking at the opposite.
Yeah.
Yeah, totally. You'll hear all about that today. That's what my talk's about. On YouTube, you always watch. Oh, I like it. Yeah, I remember.
Yeah. So you all set?
Yeah, perfect. Can I?
Yeah.
Testing. Sound good? Okay. This will advance, but it won't show up online, right?
The pointer won't show up online, but
Okay.
yeah.
Yeah, sounds good. Oh yeah, to trickle in. Yep.
an artist at Space Telescope made this bubble. Yeah, Leah Stack, illustrator at Space Telescope. She did a fantastic job. We'll see a video of this bubble later on too.
All right, welcome everyone to our session on star formation at high redshift, the first of two. And in fact, today we have a number of different redshifts of star formation to talk about. So to tell us about star formation at redshift 0 is Catherine Zucker. Take it away, Catherine.
Thank you, Mike. Yes, my name is Catherine Zucker. I'm a Hubble Fellow at the Space Telescope Science Institute. And I'm here to talk about the lowest redshift star-forming regions, the ones that are literally hundreds of light years away from us. Specifically, I'm going to be talking to you about revealing the star formation history of our solar neighborhood and our Milky Way galaxy, and evidence for supernova-driven star formation on the surface of a bubble called the local bubble. So what is a local bubble? So the local bubble is, as its name would suggest, local. It's so local that our sun actually sits inside it. So this is an artist's conception of the local bubble. The sun sits very close to the center, and we'll talk about that later. And we've known about the local bubble for about 50 years. And we've known about it as a region of lower density, of higher temperature, and of a more highly ionized states. But what we didn't know is the relationship between the local bubble and all nearby star formation near the sun. So again, this is the sun, this is the surface of the bubble. And then all of these gas clouds and these star clusters are the most nearby star-forming regions to our sun. And what I'm going to talk about today is that all of these star-forming regions formed due to the supernova-driven expansion of the local bubble over the past 14 million years. So just to contextualize you in our galaxy, so this is an artist's conception of the Milky Way. And then we're going to zoom in to the solar neighborhood. You can see the sun right here in yellow in the center. This is a 3D model of the local bubble. And now all these star-forming regions are shown in the squiggly green lines. And so you can see very clearly here in 3D that all of these star-forming regions lie on the surface. This has only become known in the last 12 months or so, because it's been very difficult to find true 3D spatial models of these star-forming regions and also true 3D spatial models of these cavities in interstellar space. And so just to get to the end of the story first, to see where we're headed, the first main point of this talk is that we can now reconstruct a high-resolution 3D model in space, motion, and time of nearby dense gas and young stars. And when we have all these components, we find that the local bubble is responsible for all star formation within a few hundred parsecs of our sun. So what has made this all possible? So this is thanks mainly to a technique called 3D dust mapping. 3D dust mapping uses the effect that dust has on stellar colors to map its true 3D distribution throughout the Milky Way. So we've been able to map dust in 3D for about a decade, but this field hasn't enjoyed a renaissance due to Gaia. So essentially knowing exactly where a star is, whose light is being reddened by the dust, gives huge distance resolution boost to these 3D dust maps, and thus true 3D high-resolution views of the interstellar medium. So this is showing you the range of spatial scales we can now probe with 3D dust mapping. So on the left-hand side, this is a 4 kiloparsec top-down view of our solar neighborhood. The sun's at the center. This is actually a section of the local arm of the galaxy. And then we can actually zoom down into individual molecular clouds in 3 spatial dimensions. So this is showing you a cutout from the 3D dust map of Leica, Glatzla, and Ensla in 2020. And what we've done is we've gone through and analyzed and extracted the exact 3D positions of these clouds to 1 parsec spatial resolution, and also their properties and their motions as well. So how do we get their motions? So we know exactly where these clouds are in 3D thanks to 3D dust mapping, but that doesn't get us its motion as well, and we want to know how this cloud is moving in 3 spatial dimensions. And so fortunately, we can actually use embedded young stars in these clouds as proxy for the motions of the parental clouds in which they were born. So this is a cutout of a molecular cloud near the sun in 3D. The gray is the gas density distribution. And then you'll see a little cluster of yellow points. That's a 1 mega-year-old embedded star cluster in this cloud. And thanks to Gaia, we actually have proper motions and radial velocities for these young stars in this cluster. And so we know exactly how this cloud is moving in 3D. Unfortunately, we can't measure the proper motion of the gas directly. But because these young stars have not strayed too far from their birth sites, and they share similar radial velocities to their parental cloud, we can use them to trace the motions of these clouds over time. And so basically we combine these two things, the 3D spatial positions of all these nearby molecular clouds, and also their 3D space motions. And so what we find is not only do all these nearby star-forming regions lie on the surface of the local bubble, but their young clusters in 3D show evidence of expansion outward from the center of the bubble. So this is what you see here. On the left-hand side, this is a top-down view of the local bubble. The sun's in the center, purple is its surface. All these squiggly colored lines are the star-forming regions, and all these arrows are the 3D space motions of their embedded young clusters. And so they all lie on the surface, and then their motions of their clusters are all pointed outwards away from the center. And so the clear implication of the combined morphology of these clouds and their kinematics is that all of these star-forming regions have been swept up by the expansion of the local bubble over time. So we know the 3D positions of these stars and also their space motions. We can trace them back in time in a galactic potential and reconstruct the history of star formation near our sun. And what we find is about 14 million years ago, these powerful supernovas started exploding. That created a shock wave, and eventually the shock wave radial velocities become important, and right behind the shock, you get an expanding dense shell, and that swept up gas in that snowplow phase will eventually fragment and collapse and form a new generation of stars. So that's what you're seeing here. Superbubble starts forming, and then you'll see the swept up gas and then star formation on its surface over the past 14 million years. So that was just a cartoon, but we can actually show the real data. So on the left-hand side is the cartoon, and the right-hand side is the real data. And so critically in the cartoon, we can show both the gas and the stars. But in the real data, we only know the motions of the young clusters over time. We can only trace the backward motion of the young stars. But essentially, given that they all seem to be moving outward from the bubble, and they're all on the surface in the present day, we can actually use their backward trajectories to model the bubble's evolution as a function of time, because we know exactly what the ages of these clusters are and when and where they were born in the galaxy. And so we assume that the bubble is entirely driven by supernovae, and we fit for the expansion of the bubble as a function of when the first supernova went off, what the ambient density of the ISM was at the time of the first supernova explosion, and then also how frequently the supernova went off to power its expansion. And this is what we get for the evolution of the bubble. So this is showing you expansion velocity of the bubble over time, its shell radius, and the momentum injection per supernova. And so this is showing you from left to right the bubble's formation to the present day. And so we find in the present day, the bubble is not expanding too rapidly. It's only about 7 kilometers per second. The shell radius is about 165 parsecs. And then the momentum injection per supernova is several times 10 to the 5 solar masses kilometers per second. And so putting this together, the 3D space motions of the clusters and also the bubble's evolution, we get that about 15 or 16 million years ago, these two massive clusters formed called Upper Centaurus lupus and Lower Centaurus crux. And what's very fascinating about these two clusters is they were at the exact center of the bubble where it should have been when it first started forming. And I'll talk about this in a second, but we think that those two clusters had enough supernova to power the expansion of the bubble. So we think we actually know the progenitor cluster that formed the local bubble. And so supernovas start going off in these clusters, and the bubble expands. And then in these different snapshots, you'll see that these little dots appear on the surface. That indicates that a cluster was born at that time in that position, and that gas was converted into stars. And so I'll keep going forward, and you'll keep seeing things form on the surface, these little dots, these young stellar clusters are forming, until eventually we get to the present day, where you have dense gas and young stars enveloping the local bubble. So as I said, we actually think we know the local bubble's progenitor population. There are two very famous clusters in a nearby association called Scorpius Centaurus. And if you actually model their present-day stellar membership and do a population synthesis modeling, you find that these two clusters probably produced about 14 to 20 supernovae. And what we can actually do is see whether this is realistic, given the total amount of momentum in the local bubble shell in the present day. So essentially, there's been a finite amount of mass that's been swept over time, and then we also know the velocity of the shell. And so we can figure out the shell's present-day momentum, and we can figure out how much momentum needed to be injected by supernova, and we can compare those two numbers. And what we find is through our momentum analysis that about 1.4 million solar masses of gas was swept up with an expansion velocity of about 7 kilometers per second. And so we find that it needed about 15 supernova to power the expansion and account for the current momentum in the shell. And so those two numbers agree, and that's great. We know the progenitor cluster. So how did the sun wind up in the bubble? That's a great question. So actually, you can actually trace the motion of the sun back in time as well. And we find that when the bubble first started forming, the sun was actually around 300 parsecs away. So it was nowhere in the vicinity of this explosion. But then we calculate that about 5 or 6 million years ago, the sun crossed into the bubble, and it now sits very close to the bubble center. And so we're just a very fortunate interloper in this whole sequence of events, and we happen to lie near the center of this bubble in the present day. So the other question people always ask us is, what does this mean for life here on Earth? Does it have any effects on Earth as we pass through the shell of the local bubble? And it actually does have some effects. And essentially, this timeline of the sun passing into the local bubble, or about 5 or 6 million years ago, is consistent with supernova iron deposits in the Earth's crust. So essentially, there's an iron isotope called iron-60. It's a radioactive isotope with a known half-life. And it is not produced naturally here on Earth, but it is produced very frequently in supernova explosions. And as these supernova go off, the iron-60 gets incorporated into dust grains. And if you pass through a dense cloud, you can actually shrink the heliosphere around the solar system and actually deposit the iron-60 here on Earth. And so people have actually gone ahead and measured the influx of iron-60 as a function of age in the past. So this is on the y-axis iron-60 influx from Wallner et al. 2021 as a function of age. And so we find that they find that there's 2 peaks in the iron-60 signature. And so, and so again, one way to actually create this iron-60 signature is for the sun to pass through a dense cloud. And so based on our modeling, we find that the sun passed through the bubble's dense shell about 5 or 6 million years ago. And so as it passed through the shell, it could have shrunk the heliosphere and then deposited iron-60 here on Earth and accounted for this peak in the iron-60 about 5 or 6 million years ago. And so in conclusion, we find in the present day, almost every single nearby young star lies on the surface of the local bubble. And in doing so, by tracing back the history of star formation, we can explain how all of these star-forming regions evolved and formed over time. We find very robust 6D, 3D position, and 3D velocity evidence that supernova can sweep up gas into dense clouds that ultimately form new stars. This has been around for 50 years, seen in theory and numerical simulations. We can show it in 6D. And then the sun's luck centered in this bubble suggests that these bubbles must be everywhere. And indeed, we're working on mapping out these bubble distributions in our galaxy and trying to figure out how they interact with each other in the past and in the future. And with that, thank you for your time, and I welcome any questions.
Yeah, thanks for the great talk. So I guess what I was trying to understand is in this model that you have for the star formation, what causes the star formation to be so anisotropic in the sense that why is it just happening in 2 directions? Is it like running into some existing stuff that was already there? Like there must be something else that's causing that, shape.
Yeah, so that's a fantastic question. And so I didn't have time to show this, but the local bubble is actually, it went off in between a spiral arm and a spur of the galaxy. So on one side you have the local arm of the galaxy, and on the other side you have a spur. And so this bubble is actually expanded into the existing spiral structure of the galaxy and formed like these arc-like morphologies. And so it's not just sweeping up sort of an ambient density, but it's carving out cavities in existing like neutral gas. And so that's why you see enhancement of star formation on sort of an isotropically, because there's existing overdensities that it's pushing the gas around and transforming into stars.
And so both of these regions are in the galactic plane, like the arms. Okay.
Yeah, it's on the galactic plane. So you can see sort of like a ring in the galactic plane, and there's no star formation at high latitudes. And people even argue that it could be a galactic chimney, and that there's no top or bottom to the bubble. That's a great question.
All right, any questions in the chat? No, I think I saw yours go up. Thanks, that's really amazing work. I was wondering about because what I understood is that all the data is just from those regions, right? So where do you get the shape of the rest of the bubble that you're showing?
Yeah, so the shape of the rest of the present day bubble. So you'll notice that I'm modeling the spherical expansion as a function of time in the past, and the present day it gets like bumps and wiggles. And so there's different ways to sort of map out the present day morphology of the bubble. The one I showed you here is looking at sharp changes in the gas density. So it's sort of mapping the local bubble as an underdense cavity. But there's different ways you can map it. One of the ways is to look at stellar absorption features and see whether the gas in the bubble is neutral or ionized. And so there's different ways. People also use X-rays, but we've compared the shape of the bubble in the present day from a number of different tracers and find that the regions lie on the surface, the star-forming regions lie on the surface in all of the different methods. This in particular is tracing the bubble as an underdense cavity.
So even not in the plane of the disk?
Yeah. So it's like, it basically looks at, the bubble's not mapped as like an absolute sort of gas density change, but it's like differential changes in extinction. And so in the plane, it'll look at very sharp changes from basically no gas or dust to like very high gas and dust. And at the top and bottom of the bubble, it'll be very diffuse, but it'll just look at sort of saddle points in the distribution and see where you get any sort of change or turnover in the extinction. And so it's definitely not uniform in density. It's very, very tenuous at the top and bottom and very dense in the galactic plane. And this model is from Pelgrims et al. 2020. If you want the reference, I can send it to you. Yeah.
All right, we got to move on. So save your questions for Catherine. I'm sure she'll be happy to chat later. And now we have Hui Li, who will tell us about star cluster formation in realistic galactic environments.
Test, can you hear me? Good. Can exit this up. So can the online people see? Good?
Yep, we're good.
Thank you. Okay, so let's get started. So my name is Hui Li. I'm currently at Columbia. So this is my first in-person meeting, but unfortunately, this is also my last one. I'll be joining Tsinghua University in Beijing as a tenure track faculty member, hopefully at the end of this year. That's the reason why I would like to use this opportunity to thank the fellowship program, especially our leads. So specifically, I would like to thank Andy. I know I have been bothering with you for so many visa issues, and so you helped me solve all of them, and it has been a very nice 3 years, and I survived it and have been very fruitful. So thank you so much. So let's get started. So today I'd like to talk about star formation and in realistic galactic environment from a theoretical point of view. So we know that the stars or star clusters are formed in giant molecular clouds. And if you ask what is a giant molecular cloud, and if you ask an observer, they will probably send you many nice pictures of this. Oh, I should get this out. Many nice pictures of the star-forming regions. For example, this one. This is a famous one. Recently popped up from the JWST observations of the Carina Nebula. You can see all of these complicated structures. But I'm a theorist, and theorists are always simple-minded. So what we usually do is, why don't we first assume a spherical in a vacuum? So this is not a joke. This is actually what we do. So this is kind of one of the example that I did a few years ago. So we start from initial conditions of a spherical cloud, actually in a vacuum, and then we push it a little bit and add some turbulence on it. And then, this turbulent motion will lead to some filamentary structures and some hubs when the filaments are crossed. And then there are many star formations that happen in the hubs. And we put some stellar feedback processes on it, and you can see these feedback processes push out a lot of the gas, and then that kind of start to vacuum this region, and so that the center is a kind of a self-maintained stellar cluster that happen. So we actually model this type of these simulations with different gas masses and different sizes, and then varying different feedback prescriptions. And what we find is that the final star cluster or star formation efficiency of these regions really depends on the interplay between the gravitational collapse and also the feedback outward, feedback force that push out of the gas. And the star formation timescale for this type of simulation are always very short as the dynamical time or the freefall time of this cloud, which is usually around a couple of million years. However, we know that stars are not forming in isolation, and also the molecular cloud really connect with the ambient environment. And specifically, this hierarchical cascade of turbulence can be witnessed from the galactic scale, and it will all the way go down to the spiral arms, the star-forming regions. And if we really want to study the dynamics and the evolution of the molecular cloud in a realistic environment, we really have to think about which type of environments do we need to really to understand the interactions between the cloud itself and the environment. So we also know that the different star-forming regions really being affected by the galactic environment. For example, in the galactic center, we know that there sits a lot of reservoirs of cold gas, but they don't form star formation actively. So if you put this star formation rate or and the mass or the star formation rate surface density on the so-called Kinnick-Schmidt relations, we find that, for example, the galactic central region, they are really inefficient in star formation. And on the other hand, so this is a compilation of the star-forming regions in different types of galaxies. On the x-axis is the star formation rate surface density of the different patches of a galaxy. On the y-axis is so-called the cluster formation efficiency, which defines of how so what is the fraction of stellar mass that are kind of occupied by the star clusters. We find that the higher the star formation rate surface density, the larger the cluster formation efficiency it is. So this is also demonstrating that we really need to think about the realistic galactic environment to study the statistical properties of molecular cloud. So that's the reason we kind of we have to develop both the realistic galaxy formation model, and we also need to have very high resolution to focusing on the individual molecular cloud. So this is the galaxy formation model that I started with. I use the Retrieval code, which is a moving mesh hydrodynamic simulation code with the realistic subgrid models for galaxy formation, so that this galaxy formation model can, this stellar feedback can regulate this inefficient star formation and create this multi-phase ISM too, so that I can to start with. And then I design a new way of doing the zoom in so that I can put a lot of resolution elements to a specific target, a giant molecular cloud that I want to simulate with very high resolution. So the end product is a very large dynamical range radiation hydrodynamic simulations, so that the simulation can simulate the whole galaxy on a hundreds of kiloparsec scale resolution, and then zoom in to a individual spiral arms, and then zoom into these individual filamentary structures about hundreds parsec scale, and then zoom in all the way down to a kind of parsec scale molecular cores. And so this dynamic range is achieved by this state-of-the-art active refinement scheme that I developed in this Retrieval code. And you can see that, so this is a very small region. This is a very massive star-forming region that have a massive star cluster sitting at the center, and then the feedback actually triggers this kind of local bubble that's similar to the Catherine's finding. And you can actually see there's some triggered star formation at the edge of the bubble. So this is actually one of the demonstrations of the power of this type of zoom in. So I don't think I have enough time to show you all of these regions. I'll give you two examples. One on the left-hand side, this is a very chaotic star-forming regions of a molecular cloud very close to the galactic center. As you can see that the whole dynamics of this region are completely dominated by this rotation of the galaxies and the galactic shear. And these galactic shear actually pump a lot of turbulent energy into this region. And this turbulent energy is mostly solenoidal, so that it kind of prevents the collapse of the molecular gas and maintain a very low star formation in this case. And on the other hand, this is a region of a very thin filaments. And these filaments are created by the two supernovae two supernovae coming from here and here. It squeezes this molecular gas and lead to the active compression along this line. And then there are a lot of star formation happen. And then the star formation then triggers the second generations of stellar feedback that creates a lot of holes. So to put it more quantitatively, here I showed you a velocity power spectrum of different regions that I zoomed from this galactic environment. So this is the over a large dynamical range. So on the leftmost side, this is about half a kilometer, this is about a 1 kiloparsec range, and then on this side is about 0.05 parsec. So with this large dynamical range, I can start to explore what is the shape of this turbulent power spectrum and how does this turbulent cascade happen in different galactic environments. So first, I find that you really need this large dynamical range to study the shape or the slope of this velocity power spectrum, because on the large scale, it really suffers from the nitrous frequency. On this lower scale, it really suffers from the numerical diffusion. So it is only at this central region when you have this large dynamical range so that the simulation can really reproduce this so-called Berger turbulent power spectrum for supersonic turbulence with a power law of -2. However, there's a very interesting trend that if the star-forming region is closer to the galactic center, then it leads to a shallower slope for this turbulence. This is mostly due to the fact that if the galaxy patch is closer to the center, then it is more solenoidal dominated, and then this will become more shallower. So in terms of the diversity of these individual star-forming regions, you'll find that for most of the cases, these clouds are not in isolation. There are some rare cases when the clouds collapse. It's kind of in a more or less isolated scheme. But for most of the cases, the star-forming regions keep on having this very strong and long-lasting accretion materials for over tens of millions of years. So this is different from completely different from the picture of the isolated molecular clouds. So there are also some cases that you show that I find that there are some collapse or the collisions of two molecular clouds. And however, what I find is that if you have very high resolutions, this type of events becomes more kind of rarer and rarer because the feeding factors of this cold gas is much smaller than the hot gas, hot and the less dense gas. So with the high resolution, this collision rate dropped dramatically. And there are also a very interesting case that if there's a supernovae happened from this, I don't know if you can show this, if you can see this clearly. So if there's a supernovae happen from the bottom, it can completely sweep up the material of this existing molecular cloud and then evaporate it very quickly. So 1 minute. So this is a kind of the mass budget for these star-forming regions. For some of this cloud in isolation, you find the feedback from the star formation kills this cloud for only a few million years. But on the other hand, there's another extreme case that they keep on accreting the material so that the star formation will keep on going for more than tens of millions of years, which is very different from the isolated case. So here I put my final slide. So these are clouds, and they are not spherical, and they actually have to interact with the environment.
Yes, Catherine? Hi, great talk. So I'm just I have a question about the triggered star formation scenario you showed in the simulations. Specifically, I'm wondering whether when you see the triggered star formation, do you see it in like one burst or like sort of a constant star formation rate over many mega years, or are there like discrete epochs? Like sort of what's the time evolution of the star formation rates?
Yeah, so this is a very good point, and so you are the propagation of these shells, they really depends on the local environment. And then this triggering star formation also depends on how, when this, the shells hit this ambient gas. So, and we definitely see the sequence. So for example, if this, supernovae shells that hit this dense gas, it triggers this compression mode of the turbulence, and then this turbulence will have to spend hundreds of thousands of years to propagate to these star-forming activities. And then there are some star formation at this epoch. And then the shell will keep on moving, and then it kind of pop up the different regions of the high density.
But do you have like multiple compressive shocks over time?
Yes, and then they're actually they're from different physical mechanisms, because at the beginning it is the H2 region and also the stellar winds that triggers the first generations of this triggered star formation. And then when there's several supernovae happened at this epoch, then there's another secondary, another suite of triggering events. So
Okay,
they have this sequence.
Yeah, perfect, thanks. All right, we got to move on. Next up, we have Karthik Iyer, who's going to tell us about the star formation histories of galaxies.
Hello, hello. Can I share my screen?
Oh, yes, perfect. Yes, go ahead and share your screen.
All right. Are you able to see my slides?
Not just yet.
No.
One moment.
Okay.
They're visible online.
I am visible online. Okay. But not my slides yet.
Yep, we're good now.
Okay, we're good. Take it away, Karthik.
Right. Perfect. So you can see the slides and see them change, right? Great. All right. So first of all, thank you so much to the organizers for both letting me speak and for setting up the talks in such a way that this seems to be a natural progression in scale from the local bubble to regions within galaxies to entire galactic systems and ensembles, right? So my name is Karthik Iyer, and I definitely did not just spill coffee on myself. I am currently a Dunlop postdoctoral fellow at the University of Toronto, and I'll be starting as a Hubble fellow at Columbia later in this fall. I'm really sad that I couldn't be there with everyone in person, but hopefully my visa will come through soon and that can be rectified. So today I want to talk a bit about the star formation histories of galaxies and how we can measure them from observations and connect them to theoretical models and simulations to sort of get to the physics of it all. Before I go forward, I'd like to thank all of my collaborators without whom this research wouldn't be possible. And I'd also like to thank all the people who write and maintain open source software, because that really benefits everyone in the community. So thank you. All right, the way I'm setting this up is to talk about star formation histories why we care about them, how we measure them, and how we can learn more about the underpinnings of how different physical processes regulate star formation in galaxies from simulations and then get constraints on those from observations again. So the main question that I'm trying to answer is explaining this extremely large diversity that we see in galactic populations all around us. And over the last few decades, we have learned that there's a bunch of different physical processes that are responsible for regulating galaxy growth, for regulating how a galaxy accretes gas, how it forms stars, and so on. And these take place over a range of both spatial scales, as we mentioned in the talk just before this, but also over a range of different time scales. And a lot of these timescales overlap and they're not well characterized. So if we are able to get better constraints on the strength and timescales of these individual processes, we can understand a lot better their role in the evolution of different populations of galaxies. So that's what we want to do. But there's many different ways of doing this. And so the particular sort of like line of the particular approach that I took is to go in and look at the star formation histories of galaxies. And so these are essentially functions that record the star formation rate as a function of time from the Big Bang up to the point of observation. And we care about these because they bear the imprints, both in terms of overall shape and in terms of fluctuations on different timescales of the different physical processes that are regulating how star formation happens in these galaxies. So that's why we want to study them. That's why we want to be able to measure them from observations. And if you go in and you look either at measurements from the local universe or in cosmological simulations, you see that, again, like different types of galaxies have star formation histories that sort of reflect their history and their growth over time, both in overall shape and in the kinds of fluctuations that they have. So the framework that I'm setting up is to build inference mechanisms so that you can robustly infer star formation history information from observations, which usually are the spectra of galaxies, and then connect this to physics using cosmological simulations and theoretical models. Right? So that's the big framework overall. And there's a whole bunch of science that we can do when we start doing this. And I don't have time to go into this in very much detail, but please feel free to ask me about this afterwards, if anything interests you. So how do we measure the star formation histories? And this is an important question because a lot of downstream science that we do about galaxy evolution depends on quantities like stellar masses and star formation rates that are derived quantities from the star formation history. So historically, we have been using simple parametric forms like constant star formation histories or these tau models or delayed tau models to sort of parameterize the star formation history and then just derive those parameters. But there's been a lot of studies in recent times that show that this actually introduces systematic biases that sort of imprint these parametric forms on the derived quantities. So we want to move beyond this. And the way we do this is by going to non-parametric star formation histories, which don't assume a predetermined parametric form. Here's one very common example where we can bin up the star formation history in discrete chunks and then just determine the star formation rate in each bin as a free parameter. Now, this works very well for masses and SFRs, but it's not great when you want to do timescale analysis because the bin edges themselves can cause artifacts in that. And so instead of thinking of the star formation rate in a bin as your free parameter, we can instead go ahead and say that the edges of the bins themselves are the free parameters and divide it up so that there's an equal amount of the total mass that's formed in each of the bins. So this is this method called the dense basis method that I've been working on over the last few years. And it basically chunks up the stellar mass into discrete chunks and then determines the look-back times at which it formed different quantiles of its mass. And so you can see here for a bunch of star formation histories from the Illustris TNG simulation that this works very well at describing a whole variety of complex star formation history shapes. Right? And the code is available, and if you're interested in using it, please reach out to me. And it's being used in a whole bunch of different ways that I can briefly describe. So what does this get us? The fact that we are able to get non-parametric star formation histories with this very flexible method means that we can apply it to large galaxy surveys of, so here I'm showing the star formation histories across stellar mass going from left to right and increasing redshift going from top to bottom. So it's essentially showing galaxies in the candle survey and using this to build a picture of how overall the star formation histories evolve across galaxy growth and across cosmic time. You can also start looking at individual populations of galaxies that we used to consider on a statistical basis. So we used to consider all galaxies at redshift 1, all galaxies at redshift 2, and so on, and connect their average properties by connecting these different populations. But now if you have star formation histories, you can actually trace back individual galaxies in time to try and match their progenitors when and figure out what their properties might have been at these earlier epochs, instead of just talking about averages. And finally, you can start talking about the correlations between the star formation histories and ancillary properties like morphology or galaxy sizes or central densities or environments, right? And so having star formation histories sort of opens up all of these avenues of research. A few projects that students are working on. So Kate Gould is using the Cosmos 2020 survey to figure out when the first galaxies quenched at high redshifts. Caleb Lammers is looking at the SDSS manga galaxies to figure out if there's imprints of AGN quenching in the star formation histories of galaxies, and finding that the time since quenching seems to be sensitive to this AGN population. And Juan Alfonso is using star formation histories that we originally got from spectra, but instead training a neural network to predict the same star formation histories from images instead, and then turning back and asking the question to the trained neural network that what part of the image did it use to make its decision. So it's trying to find the link between the temporal and the spatial signatures of star formation. And another really fun example is when we were looking at the early release James Webb image of the SMAX cluster. We found this really interesting object called the sparkler that didn't look very interesting with Hubble, but with the Webb imaging, you could see all of these compact star-forming knots. And so we were like, are these young star-forming clusters or are they old globular cluster type objects? And so after doing detailed photometry and modeling, we actually were able to find out that a bunch of these are globular cluster candidates. And we could actually age date them and find out the redshifts of their formation. And this is really key because in the local universe, when we see globular clusters, age dating them is really hard. But if you're actually able to see these at high redshifts, then the universe was much younger and age dating them is a lot more precise. And so this allows us to put down constraints on GMC formation mechanisms and so on. All right. So all of that was with observations from Hubble to Webb. And what can we do with simulations? So simulations have star formation histories that contain a lot more detail. And so instead of just looking at the overall shape, we can actually go in and look at the power spectra and see if there are imprints of the different physical recipes that were put into these simulations in the power spectra of these galaxies.
2 minutes.
Yes, thank you. And so the key point is that if we look at any single simulation, and we take slices and we look at the mass evolution of the amount of power in star formation rate fluctuations over time, you can see these really nice trends that might allow us to construct physical models and so on. But if you take a bunch of different simulations and put them all on the same plot, you see that they're just all over the place. And this really sort of reflects to the fact that we don't have constraints on how feedback is regulating star formation histories sort of along these range of timescales, and therefore constraints, if we could get them in the space, would be really crucial to informing the next generation of simulations, but also our models of how galaxies evolve over time. So that's the last bit, right? We can take parametric forms for the power spectrum of galaxies, turn that using the Wiener-Khinchin theorem into an autocovariance function, put that into something like the dense basis method, and use it to forward model observables. So we can forward model the distributions of H alpha or H delta equivalent widths or the DN 4000 breaks for populations of galaxies, and see how those distributions change when we change the parameters of the PSD, and then try to constrain that using observed populations of galaxies. So this means that we can constrain not only the overall shape, but also the detailed covariance of how star formation happens in galaxies and how it directly ties to the physical processes. The last bit is that we have been running this thing called the Pan Survey SED Forum. This is especially in the era of large data sets like what we're going to get from Webb, but also Roman. We wanted to encourage all of the different people who work on modeling galaxies and extracting their physical properties. We wanted all of them to work together and have a place to talk. So that's the motivation behind this. There's a website that you can go see, and we've been running roughly monthly cadence talks on different topics and sort of inviting experts to talk on this. So if you know people who are interested in this, please come talk to us. If you have grad students that you want to, that you would like to give talks on this, also let me know. And I will just leave my conclusions up saying that galaxy spectra contain a lot of information about what happened in terms of its past star formation. And modeling this using techniques like Gaussian processes, we can infer both the overall shape as well as fluctuations around the shape on different timescales and use this to connect to physics. So thank you.
Time for a question or two. Thanks for the great talk. In the second part of your talk, I was a little confused when you were talking about the non-parametric models.
Okay.
Because you described how you had parameters like the time edges of the bins.
Right.
So, yeah, and so my question was, given the kind of complex structure shown in the black curve there, could you kind of directly use something like a GP or something to capture that complexity if you're just interested in kind of the overall shape of it?
So okay, that's an excellent question, and there's two parts to this. So one is that the amount of information that we have in our observables, so this is either photometry or spectroscopy or a combination of the two, is usually very limited and can have covariances with other parameters like dust and metallicity and things that we also need to fit for. So realistically, when we fit for the star formation histories, it's really hard to get more than 3 or 4 parameters out of the data, which is why I'm using approaches like this, where you can sort of try to guess as much about the shape as possible with a small amount of numbers, right? So we don't actually have access to the full black curve. We do in the simulations, but not in the observables. So that's one part. And the other part is just that this is non-parametric in the sense that the number of these parameters can be adjusted based on the data quality. So if you have higher quality data, the method automatically sort of folds in more parameters to try to get more structure. And it does use a Gaussian process for this whole framework. So that's how you get the smooth curve from the constraints.
I also have another question. Does this only work in very massive galaxies where there's just pretty much constant star formation and it's kind of sums up to be a stochastic process? Because I don't see where in dwarf galaxies, it seems quite a different situation.
No, absolutely. You're sort of bang on the money. So one of the things that we can do with this Gaussian process is put in a model for the star formation rate covariance, right? So we can essentially put in a prior of how bursty we think the star formation is. Now, this method, the way it's been built, is designed primarily for high mass galaxies that sort of have this constant thread of star formation running throughout. But as we push to higher redshifts and as we go to lower masses, we have been working on changes to this covariance function so that it can even start fitting more bursty galaxies. But we are not quite there yet.
All right, thanks a lot, Karthik. All right, so ending our progression from low to high redshift today, we have Sinclair Manning, who will tell us about near-IR dark dusty galaxies in the early universe. All right, Sinclair, you can share your screen.
Okay, can you see my slides?
Yes, we can.
Okay, great. All right, let's just get into it. Hi, everyone. My name is Sinclair Manning. I am starting my second year as a Hubble Fellow at the University of Massachusetts Amherst. And today I'll be talking to you about my work trying to understand the hidden nature of near-infrared dark or near-dark galaxies and our ongoing search to find this missing population of dusty galaxies within the first 2 billion years of the universe. So if we take a look at an image like this of the Hubble Ultra Deep Field, one might think, okay, this seems to, encapsulate almost everything you might want to study about galaxy formation and evolution. I mean, the diversity of galaxy sizes, colors, morphologies is really quite staggering. But it was eventually realized that surveys such as this, these rest frame ultraviolet optical surveys, systematically miss large swaths of galaxies, mainly galaxies that are heavily enshrouded in cosmic dust. So that dust absorbs the ultraviolet and optical light from young massive stars and re-emits it in the far infrared, submillimeter, and millimeter wavelengths. So they're effectively rendered invisible in surveys even as great as those with the Hubble Space Telescope. And so an example of this can be seen here with cutouts from one of these near-infrared dark dusty star-forming galaxies, going from short wavelengths on the left to longer on the right, starting with the current deepest observations with the Hubble Space Telescope. We see we have complete non-detections. All the way through the near-infrared K-band imaging, we still do not see a galaxy. And then it's not until you get into the mid-infrared regime of IRAC does a source begin to pop out. And then finally, your kind of smoking gun for these dusty star-forming galaxies is longer wavelength detection. And in this case, it's an ALMA 2mm detection. Okay, so it was realized that the universe is populated with these dusty star-forming galaxies. DSFGs, as I'll refer to them for the talk, represent a phase of galaxy evolution identified by the following characteristics. So they're undergoing enhanced star formation. Some are capable of forming upwards, if not over, 1,000 solar masses per year. Because of all their dust, they have very bright far-infrared luminosities. They're known to sit at a pretty broad redshift regime, redshift 1, and you can maybe put an extra twiddle at redshift 7, as that is a very active, ongoing area of research is trying to find the highest redshift dusty star-forming galaxy. And of course, they have very extreme dust obscuration. So these DSFGs have been known about for some time now, since about the late 1990s when the early submillimeter instruments were coming online. But most of those galaxies do sit at around redshift 1 to 3. And so in the early universe, we're still very unconstrained in terms of our understanding of how dust-rich or dust-poor the early universe is. And that's what's shown in the plot on the right here. This is a version of the Maddow-Dickinson plot showing star formation rate density as a function of redshift. And you can see the blue points are our rest frame UV measurements, and we're very well constrained out to extremely high redshifts. But our infrared and submillimeter measurements have been a little bit lacking. And really, once you get past about redshift 4, very little is known. And this plot is a little old. Some improvements have been made to this, but for the most part, we're still very much trying to understand how prevalent dust is in the early universe. Okay, so while dusty star-forming galaxies represent a phase of galaxy evolution, these near-infrared or near-dark DSFGs are a specific subsample of DSFGs. So I generally use this term near-dark, as we saw in the cutouts previously at the top here. These are galaxies that are not detected in our current deepest optical and near-infrared surveys. But the naming can vary in the literature depending on your survey depth and your wavelength coverage. So you'll see them called HST dark surveys, H-band dropouts, K-band dropouts, IRAC only. It kind of varies wildly. So I just use near dark to generalize across the board here. But again, you can see in the SED, you only have upper limits for your lower wavelength data, and then your like low resolution Herschel far infrared data as well. You're really anchored only by your IRAC observations, and then you're very well sampled along your Raleigh Jeans tail, observing the dust continuum. So those long wavelength observations are key here. So the survey that I'm currently using that provides us with these long wavelength observations is the MORA 2mm survey. This is mapping obscuration to reionization with ALMA. So this is the largest 2mm mosaic taken to date with ALMA, and this wide area blank filled millimeter survey is ideal for finding high redshift dusty star forming galaxies. Also, it's been found that going to wavelengths longer than 1 millimeter effectively selects for redshift greater than 3 galaxies, thanks to the very negative K correction. So that really motivated the 2 millimeter survey here. And then, although I'm talking about these near-dark galaxies, when the survey was initially proposed, we didn't have near-dark galaxies in mind. We were just trying to find high redshift greater than 4 DSFGs, and it just so happened that around a third of the DSFGs found in MORA are near-dark, and so that was when I kind of pivoted towards understanding the subsample of the near-dark population. Okay, so this is a plot I've compiled recently, just trying to get a handle on the current known population of near-dark DSFGs. This is a galaxy main sequence plot with star formation rate as a function of stellar mass. And this is basically everything I could find in the literature at the moment that lists the star formation rates and stellar masses, of course. So there are some surveys that are missing from here. And then the beige circles are the more canonical sub-millimeter galaxies, which are just DSFGs as well, but tend to be the more extreme cases lying farther up to the top right of this plot. And so the main thing we can take away from this is that we see this apparent inhomogeneity in our near-dark sources. They span a pretty broad range of stellar mass and star formation rate. So that leads to questions of the underlying populations that are subsumed under this near-dark label. Are we actually seeing distinct galaxy populations that happen to be near-dark? And again, you can kind of see in the legend these different naming and selection techniques of the dropouts versus radio-selected and so forth. So I'm just going to zoom through this list of some of the outstanding questions. These are the ones I'm kind of most interested in, but is by no means a complete list of outstanding questions surrounding this population of galaxies. So very obviously you could ask, what makes a DSFG near-dark? We believe it's probably some combination of going to higher redshift and then taking into account the geometry of the galaxy. So whether or not your dust component is perfectly coupled with your stellar component, or if there's some offset that allows for stellar light to leak out and be detected. How can we best detect near-dark DSFGs? One thing I didn't note from the previous plot, all those, that compilation of sources from the literature, the overlap between, a source detected in one method versus another is not particularly high. So again, I'm curious to know if there's a way that we can have an unbiased method that would detect all of the near-dark sources, or if, again, they're just distinct galaxy populations that you have to account for. We want to know more about their redshift distribution. The majority of these sources are all photometric redshifts that are not particularly well constrained. We believe they mostly sit, between redshift 3 and 6, but nailing down those redshifts would be really helpful. Again, are we looking at distinct galaxy populations and just calling them all near dark? What are the environments of near dark DSFGs? Are they isolated? Are they in protocluster environments? Are near dark DSFGs the progenitors of these recently discovered high Z quiescent galaxies? So we're finding quiescent galaxies up to redshift 4 now that previously we didn't know about. And so perhaps near dark DSFGs are the parent population of that sample. Do near dark DSFGs host AGN? I have no idea. I would love to know. And then will we find JWST dark DSFGs now that JWST is online? It'll be really interesting. We're hoping that JWST will illuminate some of these near dark sources, but if there were in fact also JWST dark sources, that could be really interesting for us. One of these questions that I actually have tried to address in my most recent paper was this evolutionary question of whether or not they're progenitors of high redshift quiescent galaxies. And I did this very simply through predictions based on stellar mass and number density. So this is just a closed box scenario of stellar mass growth, evolving the stellar masses of our Mora DSFGs based on a fixed starburst of like 100 mega years, as well as based on their inferred gas depletion timescales. And the main takeaway is that the masses that they end up at fall in line with the masses of quiescent galaxies. But again, redshifts and the mass estimates are very uncertain, so there's definitely room for improvement here. The other way I did this was just through a quick number density calculation, taking into account the area of the Mora survey and the number of sources. The short answer to this is that the number densities largely agree, but within the rather big uncertainties. So the top part of this plot, this is from Francesco Valentino's work, is showing the number density of quiescent galaxies around redshift 3.5 based on observations and models. And then the bottom half in blue is the dusty star-forming galaxies at redshift greater than 4, again from observations and models. And the gray band is showing roughly where the Mora sources, both when you take into account all the Mora sources and just the near-dark ones as well. So it seems like they are a likely progenitor. So moving forward, we'll be looking to answer more of these questions with ALMA and JWST data. We have the X-Mora survey. This is the expanded Mora survey coming out this October, actually. We hope to reduce all that data. So we're more than doubling the area of the Mora survey and hopefully finding around 20 or so more redshift greater than 4 dusty star-forming galaxies. And if our previous breakdown holds, then maybe around 6 of those or so will be near dark. And then, of course, with JWST, we're all very excited for the Cosmos Web survey as Mora sits in the Cosmos field. Unfortunately, I have to wait a little bit longer for this one. Actually, the top half of Cosmos Web is getting done later than the bottom half, and of course, that's where Mora sits. So hopefully we'll have this data in hand between December of 2023 and January 2024. But again, so maybe these sources won't be near dark anymore, and we're really looking to improve their photometric redshifts and derived physical properties. So yeah, in summary, the near-dark galaxies are a subsample of DSFGs, which is a phase of galaxy evolution. We're still in the super early stages of just finding and building up the senses of redshift greater than 3 DSFGs in general, and then on top of that, the near-dark version of them. These very early results suggest that maybe we're looking at distinct galaxy populations that can all be categorized as near dark. And then with ALMA and JWST, we really hope to improve upon our understanding of their basic properties like redshift, stellar mass, star formation rate. And so really the hunt is on now for the universe's first dusty galaxies. And with that, I'll take any questions.
All right, any questions from the room?
Thanks for that really interesting talk. I was wondering if anyone has looked at sort of the properties of the near-dark galaxies and compared those to, say, the population that is marginally detected in the near-IR bands, and if those show similarities in properties to the near-dark galaxies, such that it looks like there's a sort of continuum connecting the near-IR detected sources and the near-dark sources, and it's just a sort of like depth in the near-infrared imaging issue, or if it does seem like there's some like distinct breaks between those populations.
Yeah. Short answer is no, simply because we're just trying to, build up the number of sources. But even within my small sample, I see that. So I'm in two of my near-dark galaxies. One is marginally detected in K-band and is actually included in the Cosmos catalog because of that, where the other one is not. And actually, you can see it on this plot. The one that's marginally detected is the lower star formation rate, lower stellar mass one. So there's just a lot of different factors that could go on into it. Again, I'm very interested in this orientation argument of, is it really just, I don't know, getting lucky with your stellar component being slightly decoupled, which appears to be the case for this one near-dark galaxy. And then, yeah, as you mentioned, having a survey that actually has even depths across the board to even compare, apples to apples. It's really hard when we're looking at targets from different surveys with different depths. So, yes, there's a lot of work to be done.
Thanks. These objects are super interesting. In terms of the finding out which ones are AGN, is there some hope to just look at like Chandra Cosmos fields, for instance, and see how many of them turn up in the X-rays?
Yeah, so we did do that for the Mora sources, and the results were inconclusive. There was no strong Chandra detection, or like any detection really, but is that just because it's so heavily, is there an AGN that's just so heavily dust enshrouded, or is the answer is we don't know. But at least from the current Chandra data that we have in Cosmos, you couldn't say there was no detection.
All right, let's have a hand for Sinclair and for all the presenters in this session.
Thank you. Enjoy your lunch.
Where's this on this new? So there we go. What keeps happening to that map? No, that's not the map. It's the NHFP. I stuck it in there again. Did you rename it?
Yep. Everything was called NHFP.
Well, okay. No, that was. Oh no, it didn't open. Let's see. Open it? No, that's not the full opening. Yeah. It doesn't like the way I double click. There it goes. Okay. That is slow. All right. So, today we're going to meet for another picture. This one taken by a drone. So that's Well, if you don't have a drone, you're not in. It's not 2022. So, you're going to